uh, busy day. Marco. So I need a bit of silence because I have a few logistics issues to present. Okay, so happy to welcome you for the second day. I hope you enjoy your first day. Some of you just arrived today, but you had the possibility to follow everything streamlined yesterday. Maybe a few important points, because we start with a plenary, and we will, this is a quite important plenary because we want to show, we always say that the future is bright, but, sorry, the present is bright, but the future is even brighter. So you will hear about the future missions from the different space agencies. But before we go to that plenary, a few logistic points. We will explain to you just after this plenary. We'll take a bit of your time, 5 minutes, to explain how to move to the other rooms, because there are different. Some will stay here because there will be another session here. But then we have another big session in another large room, and you probably don't know where it is. And we have the demos. What I would like is that those doing the demonstration this morning, if they can come after this session and say just 1 or 2 words, let's say 1 minute each, to present your demos, so that people know what you are doing. And if that's OBIS, the Geo Global Ecosystem Atlas, OpenEO, and One in the Box. So each of you, once we are done with these sessions, come on stage and just say a few words to make an advertisement about your event, and then there will be one person from ESA for each of the room where all the demonstrations will take place, and the other oral sessions. So there will be 3 people, but we'll explain everything after this plenary. But at this point, I give the floor to Steve, who will moderate this session.
Buongiorno. Buongiorno. Thank you. As said in my best Scottish accent. So, my name's Stephen Ramage. I'm the Executive Officer of CEOS, Committee on Earth Observation Satellites. It's my pleasure to be here today to introduce our fabulous panel, who are going to wow you with their insights. This session is looking at future EO missions and their relevance to biodiversity monitoring. They're going to present on upcoming or future EO missions that will contribute to biodiversity monitoring. They're going to talk about collaborative joint efforts. They're going to talk about open and freely accessible data. And they're going to highlight major initiatives, for example, the release of archived data. So you don't hear much from me, because you're going to hear great stuff from our speakers. So I'll go first to Marco Celesti from ESA, who will talk about future optical EO missions.
Good morning, everyone. It's a great pleasure to be here and to start this session this morning. I'll try to be compliant with the requirement of 5 missions in 8 minutes, but bear with me if I have to be a bit quick. You've heard yesterday from Rune and others the many ESA developed missions which are active and foreseen in the near future. We have Sentinel-2 and 3 today. We have Chimel STM, Flex, Biomass. Nuno will talk about it, and the next generation. But which one can be the Swiss Army knife for biodiversity? Spoiler: probably none. If we look at If we look at the usual trade-offs that we face in remote sensing, certainly applicable to optical remote sensing, between temporal resolution, spatial resolution, spectral resolution, and spectral coverage, we could add as many axes as we want to this spider chart, but let's focus on these 4. and try to map what we have and what will come. Basically, we start from Sentinel-2 and Sentinel-3, where we have already a nice coverage of those different requirements from different users' community. If we add Flex, we nail into the spectral resolution. If we add Chime LSTM, we extend the spectral coverage. We add on a spectral and spatial resolution. If we move from the current generation to the next generation of Sentinels, we have even enhanced continuity for these observations. In short, that's why I was very fast with the previous slide. In short, in about 10 years' time, we will move from the left plot to the right plot. And this is an incredible amount, a wealth of data and I would say information associated to this data that can be extracted. Now, let's jump to the mission in a nutshell concept. And starting with Flex is ESA's photosynthesis mission. Rune yesterday introduced it, retrieving the solar-induced fluorescence and additional vegetation parameters to quantify actual photosynthesis and provide also physiological indicators related to vegetation stress. How? By means of two spectrometers, a high-resolution one and a low-resolution one, which is only relatively low resolution compared to the high one. Very strict spectral and radiometric requirements, a 300 meters sampling over all land and coastal areas, flying in tandem with Sentinel-3, so with a 27 strict revisit pattern. Basically, the high-resolution spectrometer is devoted to fluorescence, but we know that by using the so-called low-resolution spectrometer and a combination of those, we can delve into characterization of ecosystem function and process, both on land and on aquatic ecosystems, much more than that. Moving to Chime, the Copernicus hyperspectral imaging mission for the environment, namely, which is aimed to provide routine hyperspectral measurement over land and coastal areas in support of European and global policies. And it's really targeted at monitoring and management of natural resources and food security. These are the driver for the mission. So the main specifications are basically carpet mapping observation over all land and coastal areas, extending as much as possible. Now we're talking about covering the entire exclusive economic zone, for example. We are limited in terms of sun-zenith angle to 84 degrees, but we cover a full spectral range from 400 to 2500 nanometers with a continuous spectral sampling of about 10 nanometers, basically. All this at 30 meters spatial resolution and every 11 days geometric revisit with 2 satellites. We ensure very high radiometric accuracy, a high SNR, and low spectral and spatial misregistration, and we deliver all that within 12 hours within the realm of, let's say, operational Copernicus applications. The main user data products are, of course, top of atmosphere radiance, but most important, I guess, for this community, bottom of atmosphere surface reflectance, both over land and over water. And we have 2 products for land surface and aquatic reflectance, which will enable the retrieval of a number of plant traits, soil traits, mineral mapping, of course, and hopefully this will facilitate the production of much more advanced land cover maps, and even going into the species abundance and distribution. LSTM, Land Surface Temperature Mission. The objective is clear: provide high spatial and temporal resolution thermal infrared observations, again over land and coastal regions, again in support mainly of agricultural management services, but as we are used to for Copernicus, one thing is what we designed for, one thing is what the missions are used for. Look at Sentinel-2, for example. So here's some of the main requirements of LSTM. Have a very high 2 days revisit with 2 satellites at 50 meters, basically, with a sampling which is higher at nadir. Several bands in the thermal infrared, visible near and SWIR infrared, and again, a very short data latency to allow operational application. Strict requirements on land surface temperature in order to be able to derive then also evapotranspiration products, which can be clearly linked to ecosystem functioning. Now, Sentinel-2, you're all familiar with that. We are working on the next generation of Sentinel-2, which is supposed to fly in the 2030s. The key for both Sentinel-2 and Sentinel-3 next generation is enhanced continuity. So basically, we're building on the existing missions, but we're trying to improve as much as possible and following clear user requests. So we move from this, which is Sentinel-2, to this, which is Sentinel-2 next generation. We add additional spectral bands for specific applications. We improve the spatial resolution, basically of all existing bands from whatever is 20 to 10, whatever is 10 to 5. And we tighten some of the calibration requirements as well, and we work in strong synergy with Landsat Next, as Sentinel-2 and Landsat are already doing. Last but not least, the Sentinel-3 next generation, I focus on the optical component of it, which is now a separate mission, reference for medium resolution, high revisit optical data. The advanced ocean land color instrument and advanced LSTR basically together form a super instrument, quasi-hyperspectral in the visible near infrared and with the dual view capability of ASL-STR. There is improved spatial resolution for both of this, and OLCI is transitioning from the current multispectral 21 bands to a quasi-hyperspectral instrument, and this will enable a number of things, as you will tell me later on, I suppose. And here just a list of potential biodiversity relevant products for Sentinel-3 and GEO with a clear focus on the ocean and coastal areas, particularly on phytoplankton functional types, where this higher fine spectral resolution can enable that. And we hope to somehow start see that as a sort of prototype with Flex already. And with this, I thank you for your attention.
7 minutes, 52 seconds. Very good. Okay, now to our next colleague from ESA, Nuno Miranda, who will speak about the radar side of things.
Good morning, buongiorno. My name is Nuno Miranda. I would like to acknowledge my co-authors for this presentation. I'll talk about the present and future SAR missions that we have. So I think that I have to press next here. Yes. So I wanted to start this presentation by giving you an overview or a timeline of the major SAR missions that we have in front of us in the next 4 or 5 years, both from the Copernicus program and from the Earth Explorer program that Marco has presented. So we have here in this graph 4 missions. Sentinel-1, which is the European flagship SAR mission, for which the replenishment has started last year with the launch of Sentinel-1D, and that will continue this year, at the end of this year with Sentinel-1D. The Biomass mission, that is a fantastic SAR mission, P-band, quadpole, that will launch in April this year. And the Roselle mission, that is SAR at L-band, that is entering CDR this year and expected to be launched in the time frame of 28-29. Harmony, I won't discuss Harmony in this presentation. That is a bistatic companion of Sentinel-1. Marco has presented Sentinel-2NG. I didn't present Sentinel-1 next generation. That goes beyond that slide because we plan to have Sentinel-1G in 2034 timeframe, but it's reality. I mean, Sentinel-1G, we are doing the negotiation of the development phase right now. This is a very comprehensive and ambitious program that allows to monitor different biomes, different ecosystems, with, as you can see, a variety of frequencies, polarizations, and if we consider Harmony, with a variety of scattering process. Yeah. So just one slide on Sentinel-1. I think that everyone knows Sentinel-1, which has been and which will be the backbone mission for SAR-based Earth observation since a decade and for the next decade as well. It has a fixed and very stable observation scenario that allow to studies, as I mentioned, most of the biomes and ecosystems at high resolution with polarization diversity. And I think that as important as that is the fact that we have this stable observation scenario that have allowed to acquire over the long period of time a stable data set that is now key for leveraging new techniques like AI-based retrievals. After the loss of Sentinel-1B back in December 2021, some biomes you can see here on the plot on the top have been impacted and they are not observed anymore. And this is something that we expect to fully recover with Sentinel-1C very soon now. So with Sentinel-1C, we'll fully recover for the gap that you see, and for the rest of the world, we'll have an increased revisit. And yeah. So for Sentinel-1C, we are currently in the commissioning phase. We expect to have the commissioning phase completed by May this year. And we are working extremely hard to have a preliminary release of the data to the users by end of March, with, let's say, the use as is or use at your own risk principle. Yeah. Biomass. Biomass is the ESA 7th Earth Explorer mission. It will be launched in April this year. It's the first P-band SAR in space. So it's truly an explorer working in full parametric mode, and it's fully designed and devoted to observe the forest structures. It's planned for a lifetime of 5 years, and it will be implemented around 2 different missions. We have the TOMOSAR phase that will last for 1.5 years after the launch, that will collect stacks of 7 images, INSAR stacks of 7 images. And we have, after that, the INSAR phase for the rest of the mission, that would collect stacks of 3 images. You can see on the plot on the bottom what is the observation scenario of biomass for the INSAR phase, but for the TOMO phase, it's more or less the same. At ESA, since the time of ERS, we used to deliver only level 1 type of products, but as biomass is a scientific-driven mission, the goal here is to deliver level 2 products. And the primary objectives of the biomass mission is to deliver 3 types of products: the AGB, the above ground biomass, the forest height, and the forest disturbance. For each of these variables, we'll have a map that will be generated over every 8 months, a global map. Yeah, this is a slide that can be quick on that. This is where we the imaging techniques that we want to use to derive these 3 different variables. So on the left, you have the pulsar type of techniques that will be mainly used to derive the AGB, the PolINSAR that will be used for deriving the forest height, and we have the TOMOSAR technique that will allow us to provide the 3D view of the forest structure. Yeah, I think that we wanted to draw also your attention on the GeoTrees initiatives, which aims at creating and making available reference forest structure parameters over more than 100 reference sites that are deployed around the tropics. I think this kind of initiative is absolutely key in order to validate the products that will be out of the biomass mission, but not only, because we'll have also the NISAR mission that will have a similar objective in terms of forest. So if you are interested in having more information about GeoTrees and contributed to GeoTrees, go into this website. You'll see here. You'll have here all the information available. And the last mission that I'd like to present is Roselle. So Roselle, like Sentinel-1, is a 2-satellite, is a SAR L-band, 2-satellite constellation designed as a Sentinel-1 companion. It's located in the same orbit as Sentinel-1. It has modes that have been designed to be compatible, and also observation scenario that is compatible with Sentinel-1. Over land masses, the main observation mode that we have is the Rosella IW. We choose that name because we want to here make the link with Sentinel-1 IW, which share more similar characteristics in terms of incidence angle as the Sentinel-1 IW mode. One, I think, important point, I won't go through the details here, but just two numbers that are extremely important for SAR is the noise equivalence sigma 0, which is our sensitivity, much better than what we used to have with Sentinel-1, sorry. And also the resolution, which is, I think it's almost twice as what we have today with, twice better as what we have today with Sentinel-1, which is quite remarkable for an L-band mission. And this is due to the fact that we are flying a very large antenna. You can see here 40 meter squares antenna, which is as big as a flat, for example. And this mission is dissipating, I think, close to 9 kilowatt of power, which is enough to heat your house during the winter. So it's very, very impressive missions that we are flying here. And that will be my last slides on Roselle. The Roselle mission can be self-sufficient. I mean, you can use the data of Roselle and make all the work that you want with it. But we believe that Roselle, and that's the way it has been built, that it's really in combination of Sentinel-1, so combination of C and L band. We really believe that this combination will provide enhanced capacity to monitor biomes and ecosystems. We expect indeed a major breakthrough in several aspects or several applications like the forest structures, as L-band will allow to break the saturation that we have at C-band. In cultivated areas and also more in general land use and land coverage, and also soil moisture thanks to the capacity of L-band to further penetrate in the soil. I think also that the higher coherence that we have at L-band will be extremely important and will represent a major improvement for all the INSAR-based retrievals. Voila, I think that's it. Thank you.
And our next speaker is Woody Turner from NASA.
Thank you. My job here today is to talk about the exciting new missions that NASA is going to launch, along with these other great missions we're hearing about. A couple of things. I want to start with a couple of caveats today. First of all, to remind folks that we're space agencies up here. And by that, and there's some good and bad with both of these things, these caveats I want to talk about. As a space agency, we're looking at the Earth from space. We look at it as we look at a planet. So it means we tend to look at it top down or globally. So a lot of our products are global products. The good news from that is they're global, they're consistent, they're calibrated. You're getting the same thing when you look at this spot versus that spot on the planet. That's extremely powerful, extremely useful. The bad thing is that most products that are needed for indicators and reporting statistically or financially or otherwise are at the national level. So we have to find a way to nationalize these global products to make them useful for all types of applications, particularly biodiversity, which is so very local in many ways. So we have that challenge. The second thing to think about and remember here is that we're mission agencies. We build, operate, collect data from, fund science and applications from missions. Good news of that is we do missions really, really well. We're very good at systems engineering of missions. The bad thing is that we don't do cross-mission integration very well, with a few exceptions, one being the recent harmonized Landsat Sentinel data, which was a real triumph, where we basically harmonize data from Sentinel-2 and Landsat, which is fantastic. But that's an exception rather than the rule. So we don't really even harmonize our data across satellite missions well, much less across satellite missions and in situ data sets, which is most biodiversity data, of course, in situ data. So we need to work on that as well. Again, there's some good news out there. We've got things like data queues. We've got standards just getting started. We've got open science, which will help here. And then the big cavalry, the coming over the hill that everybody's looking forward to is AI and foundation models. Remote sensing is largely about pattern recognition, and AI is really good at pattern recognition. So maybe that'll help us, but I wouldn't think of it necessarily as a panacea. It's going to solve all our problems immediately, garbage in, garbage out. So be wary of AI, but it's hopeful. So now let me just jump in quickly to my actual talk, and that is to talk about some of the new things we've got going in the U.S. Most all of these things, I'm from NASA, so I've got a huge NASA bias, but almost everything I'm going to show you is done in partnership with either like other countries or other agencies in the U.S., like USGS and NOAA. First slide here depicts two different data sets from missions launched in the last couple of years. The PACE mission launched about a year ago. Last week, looks at ocean color and atmospheric aerosols with an ocean color instrument and two polarimeters, one from the Dutch, another from the University of Maryland, Baltimore County. The cool thing here is it's hyperspectral in the visible near infrared, so you're getting huge amounts of dimensionality of the water surface, which lets you get to phytoplankton functional types, actually maybe even taxa, phytoplankton taxa, primary producers, very important. So that's below here, and what's on top of that is data from the Surface Water Ocean Topography Mission, or SWOT, which was launched about a year before PACE. It's a physical oceanography mission looking at circulation through Ka band radar of surface height. And so, it's really good at getting mesoscale, sort of 10 kilometers and several tens of kilometers on out, mesoscale circulation, which is how stuff gets moved around, how life gets moved around the oceans. So you put that on top of that essentially biodiversity data set from Ocean Color. You've got this great combination of physical and biological oceanography coming together. SWOT was a collaboration with CNES, with CSA, with the UK Space Agency, and NASA. So just a really cool combination. Again, the challenge here, the special sauce though, is making these different missions work in tandem. And often that takes more than just pretty overlays of data. Now, PACE is also, we don't turn PACE off over the land. So it's essentially acting like a Veneer spectrometer at about a kilometer scale, getting data every day over the land surface. Think MODIS with a spectrometer. This shows you three different colors here, essentially. Green is chlorophyll A, carotenoids in blue, and anthocyanins in red. We're finally, folks, getting beyond the age of greenness. And as we're all talking about spectrometers up here, we're getting beyond the vegetation indices of NDVIs, VEVIs, et cetera. We're getting beyond greenness to look at multiple pigments on the surface of the Earth, which will help us do plant functional type, and also, again, hopefully getting into taxonomic distinction, certainly phylogenetic distinction of plants, the primary producers or service also in the water. So this is getting productivity both terrestrial and aquatic. Very exciting. These are early PACE terrestrial data. I think they've got just 51 bands written here. It's not the full spectrum yet. Those are about to come out in the next few weeks. You heard a lot about radars. This is NISAR, to be launched no earlier than April 1st. This is a NASA ISRO, Indian Space Research Organization collaboration. Combines an L-band from NASA and S-band from ISRO. When it's launched, and looking to biomass launch, we just heard about, we'll have Sentinel-1 C-band, NISAR S-band and L-band, and then soon to follow biomass P-band. So we've got 4 radars covering everything from the canopy down to subsurface water. Incredibly powerful. Biodiversity at all levels, living systems at all levels. Water equals life, as we know. So this is a really key piece of the puzzle, but it works best in synergy with other missions. Landsat Next, which is the 2030, 2031 version of Landsat. It's what we call super spectral. It's going from about a dozen to 15 channels to 26 channels. 5 in the thermal, 4 in the SWIR, everything else in the Veneer. We're putting 3, the plan is to put 3 satellites up so we get data back every 6 days. But to remember here, there's also Sentinel-2, right? We've harmonized Landsat and Sentinel. So think about this. We're going to get probably daily data. We've got a couple of Sentinels up there. We've got these 3 Landsats up there working just at the turn of the decade. So think of the power of that, getting down to, this is 10, 20 meter data, looking at the globe, mapping the globe with 10 to 20 meter data, actually every day, every other day. It's exciting. SPG, something I spent a lot of time at, surface biology and geology. This is our next generation mission as a spectrometer, the visible shortwave infrared. So think 350 nanometers, 2,500 nanometers. Then we also have a thermal component of this, multispectral thermal. The thermals to go up in 2028, or actually probably early 2029, slight revision there. The VSWR no earlier than 2032, although we're moving that to the right, or to the left, excuse me, the left, hopefully to get these two converging. Again, the synergies of spectroscopy in the VSWR and thermal multispectral, extraordinarily powerful. The thermal mission we're doing in conjunction with our Italian colleagues at ASI. Again, 3-year mission life. Let's get these two pieces back together in launch cycle. This is the next generation weather satellite, geostationary satellite. So we talked about hyperspectral, we've got spectral resolution, we've got spatial resolution coming together from commercial and also from Landsat and Sentinel, and now we've got hypertemporal, so geostationary, stares at the same space. We're putting up 3 of these. This is with NOAA, of course, and I should have mentioned Landsat Nexus, of course, with our USGS colleagues. So this is with NOAA, looking with the new OCX ocean color instrument, but also as lands. Again, it's a spectrometer, staring, so getting hourly data of the surface of the Earth, the coastal zone, mid-continent, and the other coast. Okay, so I said we do missions well. We don't do integration of missions that well. This is our attempt at NASA to do integrated missions. It's called IESO, the Integrated Earth System, Observatory. This is how we go from an Earth observing system to a common observatory, bringing together data from all these different missions. I think the special sauce here, how this is actually going to work, is the joint data systems. We're going to have a combined data system for the different missions. We're still figuring out how to do that because we typically build data systems to the mission. The second thing is joint science and applications teams, but joint science teams that will fund research and applications to do cross-mission work. So that's IESO. This is our attempt to get out of the mission box and do true integrated mission work. And then I have to shout out to an airborne campaign that's wrapping up this year. A number of folks are here: Adam Wilson, Aaron Hester, Annabelle Cardozo, been part of this, Matt Fitzpatrick, others. It's called BioScape. We took a couple of aircraft from NASA down to the Greater Cape Floristic Province in South Africa last year. Got 3 spectrometers ranging from the UV through the thermal, and then a LiDAR, and looked at this incredibly complex vegetation. So airborne is important. It helps us get ready to go to space. It also gives us fine pattern resolution. And I think that is my last slide. Stephen, how'd I do?
I hope you're all keeping up. There's going to be an exam at the end of this. Okay, now we're going to hand over to Philippe Maisongrand from CNES, the French Space Agency.
Thank you. Hello, everyone. So I'm going to present you to give you some information concerning the CNES space missions for the monitoring of and the study of biodiversity. And this talk is given on behalf of me, of course, and my colleague. I'm Philippe Maisongrand, and I'm the Biosphere Program Manager at CNES. We all know the threat that we go through, the +2 degrees by 2050, +2 million people by 2050. It means that we will need that adaptation and mitigation strategy, and we will need reliable metrics to understand and to manage the habitat. Biodiversity is one of the aspects of ecology, and the first part of ecology means habitat. And it's a good point because remote sensing satellite is very helpful to monitor the habitat. First, I'm going to go through this chart. You've seen almost the same concerning the program of the European Space Agency. Here you see the way the French Space Agency is fitting its own program. It's not the slides begin to be a little bit too stretched. How can I get rid of that? Can I have someone helping me to remove the frame? This one? No, I need to escape from that screen. Okay. Thank you. So I'll go back. And what you see here, that we try to have some kind of our own Earth Explorer mission in advance to future Copernicus mission. Here I present two examples that are Trishna, that has already been introduced somehow, plus SWOT that you previously saw. We're also involved in the Earth Explorer mission, like FLEX, like Biomass, like SMOS, of course. And I'm going to show you now two of these missions, SWOT and Trishna, if it works. Okay. Here you can see our two missions. Trishna is CNES ISRO thermal infrared imager that will be launched in 2026. It's going to provide users with surface temperatures and daily evaporation principally. While on the other hand, it has already been shown, we have SWOT that was launched in 2022 and which is devoted to the ocean, to the coastal and to hydrology monitoring. These two missions have similarities. They are both bilateral programs. SWOT is with NASA, the Canadian Space Agency, and UK. They are both devoted to the water quality and to the water quantity and quality. The two of these missions, they deal with land, with coastal and ocean water, and they are both precursor of Copernicus mission. For LSTM, Trishna is the precursor of LSTM, and SWOT is the precursor of S3NG Topo. And they both have downstream programs. And all the products of this mission will be made available through the DataTerra thematic platform TEIA, which is itself in tight relationship with the French national program for data on biodiversity. Some other examples with SWOT. We remember that SWOT is supposed to monitor water bodies that at the size of 100 meters for rivers and 250 meters for lakes. And in the end, we've seen that SWOT is also able to get small water bodies at the size of 50 meters, which is very interesting and a very good surprise. We have also seen that SWOT is very skillful, very helpful to monitor the sea ice, which is a kind of water quality. On the right part of the slide, you can see an example of surface water dynamic over the Congo River and over Manaus. It's beginning in April 24, and it's the end of the time series is January 25. And you see that with the time revisit of SWOT, you can catch this kind of dynamic, and of course it's a dynamic of the habitat, and for the living species that are there, it's very interesting. The other one is Trishna. Trishna, as I said, is CNES ISRO cooperation. It's the design driver of Trishna is the ecosystem stress and water use in agriculture, plus the hydrology for inland water and coastal environment. Trishna also has secondary drivers. The first of these secondary drivers is the urban issue. We also consider the cryosphere, the solid Earth, and the clouds in the atmosphere. It's a global coverage with a 3-day revisit at 60 meters resolution, with different observation angles, which means that conversely to LSTM, Trishna will provide users with directional surface temperature and radiances. You see on the bottom of the page the different channels that Trishna will have. We have 7 channels in the optical side of the spectrum, and plus 4 channels in the thermal part of the channels. The data will be free and open access. Level 2 would be things like groundwater reflectances, land and sea surface temperatures, plus emissivities, vegetation variables, LAI, NDVI, and so on. We have also a collaboration between Trishna and LSTM, since Trishna is the LSTM precursor, but also with SBG in terms of products, definition, ATBDs, orbits, calibration campaign, and so on. Since we talk about, there is also this international workshop that will be held at the end of the year in Toulouse in November. And since we talk about hyperspectral with SBG, I present you this slide concerning the seminar for scientific perspective of CNES that occurred the last October in Saint-Malo. And one of the principal scientific question we had on the side of continental surfaces on the land side was the socio-ecosystem and its biodiversity. And for that, we need satellites to monitor the essential biosphere variable and to characterize the marine and the coastal environment. So we had two missions that were recommended. The first one is biodiversity in first priority. It's an hyperspectral sensor between 0.4 and 2.5 micrometers. It's for the study of heterogeneous land and coastal ecosystem, plus pollution sources in the water, but also in the atmosphere. It will be a spectral band that will be 10 nanometers wide at the resolution of 10 meters with a revisiting capacity of 5 days. The 10 meters resolution of biodiversity has to be compared with SHIME and then MAP or SBG that are 30 meters as far as I remember. The other one is 3D Earth. It's a 3D high resolution 2-meter optical imager. It could provide twice a year a global digital elevation model and a very dynamic description of the 3D dimension of the ecosystem. But by that time, there is another 3D mission that is expected this year in July. It will be launched with microcarb. This satellite is CO3D. CO3D will provide us with 1 meter relative 3D digital elevation model. And its potential in 2D images is 50 centimeters in RGB plus near-infrared spectrum parts. The global coverage with CO3D will be one global DEM built in 3 or 4 years, but there will be 18 months demonstration phase that will focus on France and on the northern part of Africa. It will be the successor of the classical Pléiades, Spotset, and Pléiades Neo satellites that you all know. A small example, very quickly, if you can put yes. This shows you the capacity of CO3D for video acquisition, and due to the pointing ability of the satellite, you can do movies like that. But it's not for the pleasure to present you a movie. It's just to show you that this ability to maintain the observation of one specific site means that you increase you have an increased integrated time, which makes possible the monitoring of light in, for example, in urban areas. Here, for example, the Louvre sector in Paris. Okay, this is a summary of the principal mission concerning biodiversity. Of course, as you seen in my second slide, we have many other satellites, but we have chosen to highlight this one specifically. SWOT launched 2 years ago. Theo3D next July. Trishna 26, and hopefully we hope we'll get something in hyperspectral domain. CNES is also involved in smooth biomass and flex. We are in tight relationship with CEOs, as we will see during the next session. And we also, this is my last point, we also have we go with additional efforts concerning our integration in DataTerra and its thematic platform. Here there is a challenge of the linkage between Earth observation and in situ measurements. And among in situ measurement, there is something that is very important, which is the environmental DNA. This is all for me. Thanks a lot for your attention.
So next we are going to have a video from Osamu Ochai from JAXA, Japanese Space Agency. Hopefully the technology will work. And there we go, perfect. You can hit play on that, please.
Thanks for giving me such a nice and then great opportunity to present JAXA's activity on Earth observation missions for biodiversity monitoring. My name is Osamu Ochiai. I am working for Satellite Applications and Operations Center in JAXA. I'm going to present JAXA's Earth observation mission at present and future with indicating potential relevance to biodiversity and ecosystem research and applications. The slide shows our mission for operating Earth observation systems. We have 4 major types of physical parameters observing through 8 operating missions. Greenhouse gas monitoring by GOSAT series, cloud aerosol base station by GCOMC and EarthCare, forest disasters by ALOS series, precipitation water cycle by GCOMW and GPM. You may be of interest the recent successful launch of ALOS 4 last year. The first slide image has been already released, as you can see on the right down side. We are excited to acquire such data streams, which is able to acquire 200 kilometers swath wide, better than ALOS 2 Pulsar 2, with maintaining the spatial resolution in 3 meters. You can see how wide it is. We are still under validation of its data, but as soon as finished, we will release hopefully next few months. I know many researchers are keen to use the data for ecosystem extent analysis and maybe more. We are expecting how to cooperate with you in future. We have a long history of L-band SAR since 1992, JS1, and then ALOS series. Our data streams allow to more than 25 years annual forest cover map worldwide. This data stream allows to monitor how much forest can be degraded around the world in past years, which should be relevant to biodiversity ecosystem. Another major data set, we are generating Global Mangrove Watch since same time frame of the forest. The Global Mangrove Watch provides fine resolution as 25-meter geospatial information about mangrove extent and changes to Ramsar Convention, national wetland practitioners, other decision makers such as SDGs indicator, and also the NGOs. Annual change information on increasing or decreasing mangroves can be identified by color. This map surely contributes to the ecosystem extent and biodiversity. We are currently developing high-resolution land use and land cover map in Southeast Asia by combining GCOMC SGLI coarse resolution and also higher resolution ALOS 2 Pulsar 2 data sets. The map is 25-meter resolution with 15 different categories of land use types. Also generating this type of data is relatively complex and burden. This information would contribute to ecosystem and biodiversity, particularly Southeast Asia region as a quite diverse area. We are expecting topography is also a quite essential data set for the various type of applications and modeling. The digital service modeling datasets with 5-meter resolution is a commercial basis, while 30-meter resolution is free and openly available from download website, as you can see. Topography datasets generally used for the baseline product, but maybe we can combine with other datasets for higher value-added products. This is a global rainfall map product, so-called the GS map. This is hourly updated and near real-time data sets. Where are the rainfall in the world? This product has huge opportunity for applying many types of applications such as flood risk assessment, agriculture monitoring, water cycle, energy and climate change assessment, and maybe even more. It will be highly expected to use biodiversity ecosystem monitoring in very near future. We also have many other potential of interest products in land and ocean globally. On land, we have a thick land products such as NDVI, land surface temperature, above ground biomass, leaf area index, and maybe more. And for marine, we have chlorophyll A, fish surface temperature, and others, which are all research products, but you can access online through our website called JASMES. I would like to especially stress our products monitoring marine ecosystem for coral reef monitoring. Because we do not have enough observation networks in ocean, apparently, it will be essential to monitor use by satellite with combining different variables, such as the simple RGB images with more physical parameters such as SST and chlorophyll A as example, in order to understand the trends and the development of the model in order to predict this local area in future. My final slide showing about future missions is currently under developing in JAXA. We have currently new 3 missions. One is a space-based LiDAR mission we call the MORI. It will be installed in the ISS in 2027. Second one is a precipitation measuring mission we call the PMM. This is a follow-on mission of GPM, Global Precipitation Mission, jointly with NASA. It is for the simulation modeling, weather forecast, and extreme rainfall, climate change, and heavy snows monitoring. The third one is the next generation optical satellite missions, which is a system of systems collaboratively with private sector. JAXA is going to develop a single LiDAR satellite system, while the private sector is going to develop a small constellation optical satellite system. Those data streams can combine to produce with high precision of 3D information. Of course, this new mission is contribute to the various type of application, including a biodiversity ecosystem. So really grateful to cooperate more in the future. Thank you very much for your kind attention.
So I'll say arigato gozaimasu on your behalf to Osamu. And now Lucy Luciano from the Canadian Space Agency, or the Agence Spatiale Canada.
Hello, everybody. Good morning. So I'm pleased to present to you, give you an overview of how the Canadian government is taking a holistic approach to address some of the actions related to nature. So I'll walk you through a few of the missions that Canadian missions were involved in and some of the applications related development opportunities we have ongoing right now. So to start with some context, the federal government of Canada released its national nature strategy last June, and in it includes several references to satellite Earth observation, both in terms of upstream sources of data, as well as some of the R&D and more operational applications developed by these data sets. And these really span, across the several targets that are indicated in the Global Biodiversity Framework and adapted to the national situation. So we have, for instance, Target 1, RadarSat, our RadarSat constellation missions, which have been recognized as playing a key role in terms of undertaking baseline mapping for spatial planning and effective management. Many such examples are actually provided in a Canadian showcase that we presented last October while we were hosting the CEOS plenary. So in that document, you can scan the QR code. You'll be able to see many government-led, government-funded projects and some missions and how these align to some of the targets and measurements of essential biodiversity variables. So in terms of our satellite systems that we're involved in, I just want to highlight a few of these. First and foremost, the RadarSat family. So Canada has been leading in terms of radar development systems for now 30 years. So we have a strong legacy in C-band radar. RadarSat-1 is now retired, but for RadarSat-2 and RCM, the RadarSat Constellation mission, are still active. And the capabilities have really increased with each generation, so both in terms of spatiotemporal coverage, polarization, in October 2023, the government announced a Canadian $1 billion investment for RCM RadarSat Plus. So RadarSat Plus will comprise of a replacement satellite. Currently, RCM is a 3-satellite constellation, so RadarSat Plus will include the design, development, and launch of a replacement satellite, and also the design of a next-generation system. And so that it won't be in 2025 launch exactly, but that's in the works right now. And yeah, so RadarSat, the RCM constellation, is currently used by a number of our government departments, the Department of Fisheries and Oceans, Natural Resource Canada, Environment, Climate Change Canada, Agriculture, etc. And so that is used to collect and report on a variety of environmental data, as much on land as well as at sea. Our next mission, WildfireSat, so that was just announced last Friday. There was, it was revealed the contractors for this new, unique fire detection monitoring satellite will be designed and constructed by Spire Global and Aurora Tech. So this will be a 7-satellite constellation. Effectively, they will build 10 satellites, a couple of spares, and a demo. And it will be the first publicly owned fire monitoring service by government. And really essential, I think, here is the orbiting, the orbit that will be able to detect fires at their peak burn time, which is usually in the late afternoon. And obviously, Canada has a lot of forests, a lot of forests that are key habitats for many species. So this will be aligned, I think, with some of the Target 7, Target 8 of the national strategy on linking climate change and pollution with biodiversity. We also have in planning the TSMM mission, which is a terrestrial snow mass monitoring mission. This will be in KU band. And what's interesting here is the relationship with snow water equivalent and links to maybe some of what Philippe was mentioning with the SWOT mission as well. These are key potential data sets for indicators on snow water, on water quantity, which again are key information pieces, especially in Canada with the amount of inland waters that we have that represent key habitats for a number of species. In terms of some of the RadarSat data that we have, so we have RadarSat-2 is operated by our partner MDA, but the Government of Canada has access to a large number of archives that were taken over the circumtropical region over the past decade. So what we're planning on doing right now, we're finalizing some of the pre-processing of this large archive, and we plan to make this data available in the coming months, hopefully, so that it becomes available to the science and research community. We realize that this data set has a lot of key qualities. It's very high resolution, and there's a number of potential new applications and research areas that can be offered to the community for various technical or application reasons. So we hope to have this launched in a couple of months, and if you're interested, feel free to contact me for a bit more information. Now moving on to more of an applications side of things. So the GBF, as you know, has set this global framework for national governments to halt and reverse biodiversity loss. And our applications development team at the CSA, Smart Earth, has initiated, has created the Nature EO initiative, which is really there to support the national nature strategy and nature protection agenda in line with this GBF structure. So the Nature EO framework bases itself on the targets and categories and indicators that are in various stages of development across Canada. And these touch on supporting ongoing science-based applications development and affecting various stakeholders and domains. We want to also take an approach where standardizing, monitoring, reporting, verification, and things such as environmental impact assessments make sure that these integrate satellite EO. And we want to also ensure that the data value chain related to biodiversity data is more accessible and mainstreamed to maximize stakeholder engagement. And one of the first activities related to our Nature EO initiative is an announcement of opportunity that was released a couple of weeks ago that's still open. It's called SAMBA, Satellites Mobilized for Biodiversity Actors. So this is really a sensor-agnostic capacity development funding call, $5 million contribution-based funds that will support up to 20 projects. And the projects must consist of at least one or more of the following research agendas. So again, advancing scientific knowledge on particular ecosystems, streamlining processes and standardization capabilities, and developing user-friendly tools and solutions for mainstreaming EO. And in parallel, we will also be launching next week a broad consultation on the use of EO for biodiversity. And that will help us refine the next steps of our Nature EO initiative. So it is a little Canadian focused, but we're very happy to have inputs from beyond, as some of the questions touch topics that are broader than Canada. And that's it.
Okay, Lucy. So our final presentation from Adriana Parra Ruiz, who's not actually Australian, but she's here on behalf of CSIRO.
Hello, everyone. My name is Adriana Parra, and on behalf of the AquaWatch Australia team, I will be presenting a very short summary on this CSIRO mission. So similar to a weather forecast app that you use on your phone, AquaWatch aims to develop a monitoring and forecasting system capable of providing near real-time updates and forecasts on water quality. So this CSIRO mission is driven by very urgent needs related to water quality monitoring of both inland and coastal waters. In particular, the need of human access to clean water and sanitation and the rapid degradation of aquatic ecosystems. To contribute to these objectives, AquaWatch aims to sustain different end users, such as countries contributing to their sustainable development goals or different stakeholders working towards sustainable use of aquatic ecosystems or conservation projects. To achieve these goals, AquaWatch will integrate a dense network of in situ sensors with air observation data. An advanced data analytics platform will be used for processing, storing, and distributing the data, and for constructing environmental models for scaling up the in situ measurements using the air observation imagery. So basically, AquaWatch is bringing together all these different technologies into one big system. And then this is a very ambitious aspect of this image, where we have this collection of different components tailored for monitoring and forecasting water quality. And to do this, AquaWatch is reaching out to different partners to make sure that the mission is driven by end user requirements and that it is informed by science. So as part of the initial stages of the mission, the AquaWatch team has deployed pilot sites across Australia and internationally. These sites include a monitoring station that has a sensor developed by CSIRO called Hydrospectra. This is a low-cost optical sensor that measures the spectral reflectance of water. And the sensor is used for high-frequency monitoring of water quality, and also for calibrating and validating the air observation data. Different modeling approaches are then used to scale the in situ data to the spatial scale of the air observation data, and for estimating temporal variations in water quality that occur in between the air observation measurements, and for forecasting. So finally, the outcomes from these environmental models are presented to the end users with a customized web map service, similar to what you're seeing on the screen. So AquaWatch is a very ambitious cross-organizational program that aims to bring together different partners from research, academia, industry, and the government sector to co-design these pilot sites with the goal of producing a very robust monitoring service that can cover the needs and the objectives of different end users. These partners include local experts and local communities that provide local knowledge and information on their data requirements for decision making. These partners also give the AquaWatch team feedback on how to present the data and how to distribute it, so that it's easy to use and easy to access. As I mentioned before, the team has deployed some pilot sites in Australia and internationally. And some of these sites are specifically tailored for assessing biodiversity and ecological issues, such as seagrass and coral reef mapping, monitoring aquatic invasive species, and mangrove forest water quality, among other projects. As for the air observation input data, AquaWatch will leverage current and future missions from different agencies to inform the environmental models for forecasting. So you can see some of the examples of the missions that are being considered for the mission. Additionally, the team is also working on developing new sensors and technology specifically tailored for water quality monitoring. And this work focuses on 3 specific topics, which are harmful algal bloom detection, monitoring of invasive aquatic species, and coral reef mapping. So you can see on these slides the areas of the spectral that are not covered by current missions, and that was the team is focusing on. As part of this development work, the AquaWatch team has produced 2 different projects. So the first one is AquaSat-1. This is a mission concept developed together with NASA's Jet Propulsion Lab. The project evaluates the instrumental and operational requirements for a new satellite or a constellation of satellites to monitor water quality across different targets in Australia and the Western United States. The second project is called CyanoSense. This is a hyperspectral imager for low Earth orbit that was designed for differentiating harmful cyanobacteria from other algae. The sensor was launched to space in June 2023 for initial stage testing. So to wrap up this presentation, I would like to invite you all to visit the AquaWatch Australia website and to contact the team if you have any questions or if you have inquiries on how to co-design some of these pilot sites. Thank you.
Thank you very much to all our panelists. Unfortunately, we don't have time for any questions, but you can take a photo and then stalk them through the conference. Okay, I'll hand back over to Mark. Thank you.
Yeah, there's a few logistics points that I want to share with you. Anyway, one point, I hope that you enjoyed these sessions. Unfortunately, we had to squeeze every presentation is 8 minutes. There was a lot of materials in these presentations. All the presentation will be shared with you. They will put on the website. We'll put the point of contact, so you have the possibility. We apologize for not being able to take any questions, but you will have all the means actually to further investigate on all of this. But you see what I said in the beginning, that the present is nice, but the future is even brighter. So a few, because now we are going to split into different rooms, and we need to guide you a bit in all of this. So we'll start 2 oral sessions in the 2 big rooms. I don't know if I have the possibility to move. Now, one very important point. Everything is delayed by 15 minutes. So we'll start in what is it, 10:15, the next sessions, and the same for the break, for the coffee break, and the same for the lunch. The coffee break is here, so you need to, even if you move to other rooms, those will move in the Magellan. Maybe I go on this one. The Magellan, which one is it? B1. Those moving in B1 will need to come in this building to get the coffee. You will not find any coffee in the Magellan. The Magellan is the other big room, with the big room. So what you see in green are the 2 big rooms, so enough space for everybody. So up to you, if you want to stay here, you can go in the other ones. I think the 2 sessions are very interesting. One on ecosystem extend, this is here, and the other one on ecosystem trades, that's in the Magellan. We will have also, that's the first one, then we have a break. You come here for the 30 minutes breaks, you come here. And then we have, in the big hall, is a session on conceptual approaches to biodiversity, so new ways to do so let's say some presentations that shares a bit new ideas about biodiversity monitoring, and also some specific topic like Arctic biodiversity, which doesn't fit into any presentation, any sessions, but it's important to show it to you. And the other one in the Magellan will be on ecosystem functions. So basically in Magellan, it will all be about ecosystem traits, structure and functions. We'll have 4 demos. In the small rooms, in rooms of a capacity between 30 and 40. So what I would like is that each of them, if you could come now, and just in 1 minute, because we have not much time, to present your demonstration. So the very first one is Born in a Box. If somebody from Born in a Box can come here.
Thanks, Mark. So Born in a Box is a software platform by GeoBon that allows to share and use analysis pipelines that transform the raw data into relevant essential biodiversity variables and indicators. Whether you work at the city level all the way to the global biodiversity framework, it could be useful. And as we heard yesterday, there is a need for countries to own the process, to be able to do the transformation themselves instead of using global things. Born in a Box could help. There's also a need to have standard processes to compare across country. Born in a Box can help for that as well. And if you want to unlock the untapped potential of EO, like was mentioned also yesterday, Born in a Box can help for that. So if you want to hear more about the concept and see how it works, well, it's a demo, right? Well, have a short walk outside on this bright sunny day and join us in James Cook.
Thanks a lot. Thanks a lot, Jean-Michel. So Born in a Box will be what we call the James Cook. James Cook is next to the Magellan. Huh? So those going to the Magellan will have the James Cook next to it. Huh? So that's the green area that you see on this screen. So the next one, maybe Obis Isilas? Yes.
Hello. So I'm from OBIS. So OBIS is the Ocean Biodiversity Information System. It's the major global biodiversity repository for marine data. And so I'm going to show you how you can access this data, how you can integrate this data with other products, and probably do very great stuff using remote sensing. I think that's all. Yeah. And we have free stickers if you arrive in time.
That's so good. Yeah, okay, you have to. You have to decide which stickers you prefer. Obis takes Claire in the building 15. Yeah, needs to move, which is the orange spot. Well, you need to be guided here. Ula, oh, you do it, Federica? So Federica, those who wants to go to, I guess, the marine guys, I mean, if you want to go and attend the Obis demonstrations, you'll go with Federica. Mm-hmm. Then we have a coffee break, but I think it's better already to present the next one. So in the James Cook, it's the Global Ecosystem Address. So David.
Hi, good morning, everybody. I'm the project manager for the Global Ecosystem Atlas. At the demo today, we'll be giving a brief overview of what the Atlas is, and then we'll be going through the data and the science together, and it'll be a chance for you to give your feedback, to critique what we're doing. You can say nice things as well, but you can also give comments. We're right at the beginning of the project, so we'd love to get that feedback. Sadly, we don't have stickers, but look forward to seeing you all there. Thank you.
But I'm sure you have other good reasons, actually, to attract the people in this. No, this is really an excellent project. And then the OpenEO. Is there anybody from OpenEO in the room? Okay, maybe they will come later. So OpenEO will also take, it's a data platform that ESA is doing, following open source. And then now we have a lot of activities actually connecting, for example, OpenEO to Bon in a Box. So I think it's important for you, if you want to know more about the data platform that ESA is supporting, please come to this OpenEO. So it's in building 15. What else? I think I said everything. Oh, yes, in the workshop. Yeah, see, the workshops, so 2 of the workshops will take place in the big hall, so there's plenty of space. We will use the flip charts for the splinters. So if, we try to put the generic type of workshop in the big rooms, and the more specific one in the small rooms, because the small rooms have a capacity of 30 to 40 people. So the rule is first come, first serve. We will not be able to have more people than seats available in this room. So if you really want to go for the demos as well, it's the same. But for example, the 3 workshops that will be in small rooms will be on ecosystem accounting, farmland biodiversity, and indigenous local community. You need to go quite early into these rooms in order to have a place. And maybe that's the last one. The people from indigenous, organizing the indigenous workshop wanted to say something to introduce their workshop.
Buenos días con todos. Les traigo un saludo cordial de la Amazonía ecuatoriana. Yo soy Mario Vargas, soy de la Nacionalidad Shuar de Pastaza.
Good morning, everyone. I greet you from the Ecuadorian Amazon. My name is Mario Vargas Shacaim from the Shuar Nation.
Quizás pueden ver en la foto, es en África, pero muchos dirán que no es Amazonía. Entonces, vengo de África, de un pueblo Samburu, de Kenia, para mirar también cómo ellos están viviendo en sus territorios en comparación en lo que estamos viviendo en la Amazonía.
As you can see from the picture, that's not the Amazon, but it's an indigenous tribe in Kenya called the Samburu. And I just came back from the Samburu tribe where I was working with the community there.
Podemos notar también que los científicos nos han dicho, si nosotros no nos preocupamos por nuestro planeta, puede pasar en la Amazonía lo que está pasando en otros lugares.
The scientists have warned us if we don't protect the Amazon, the ecosystem could look like this.
Hago un llamado a la comunidad científica, a la academia, que podamos unir esfuerzos ideales para poder cuidar nuestro planeta, porque tenemos a otros hermanos en otras partes, también como en la Amazonía, los efectos del cambio climático en nuestros pueblos amazónicos.
I urge the scientific community to work together because there are other indigenous communities worldwide that are already at the forefront of climate change. So we need to work together to find solutions.
Quiero agradecer a los organizadores de este evento y también más tarde tenemos un evento en donde pueden participar para los que tienen iniciativas de proyectos puedan compartir y podamos innovar nuevos proyectos en bien de nuestro planeta. Muchas gracias.
I would like to thank the organizing committee and invite you to come to our workshop to co-design new innovative projects. Thank you so much.
So this workshop will take place in the building 15 in the afternoon. Of course, it's one of the small rooms that we have on that side of the inside. So I think, yeah, we're already very late, so it's time to move to the other rooms. I want to give a round of applause to the speakers of the first sessions. And see you in the other rooms.
Again, how do you do? It's fine. Yes.
Did you just get here?
Yeah, I just got here yesterday, and so it's still live. Yes.
It's good? Publishing like wild.
No.
I'm going to be rude here. So from the user perspective, we can expect that we will continue to have data. Yeah, we need two, or we have another here. So 1 minute or 8? That? So will be 1 minute.
the 1 minute is something to say exactly.
Yeah, but 1 minute to 10. No, 1 minute to 10. Oh, no, okay. So we need another? Voilà. And the others are city. Very interesting, thank you. That would be nice because it makes it faster. The thing is, okay, we have okay, I'm going to open my
I think it would be difficult to classify. Yeah, but there is another one there, I think.
We still have another session.
The lunch, then probably it's 90 minutes.
Yeah, we have a bit of time with the lunch.
If the sessions are scheduled, finishing a little bit, not exactly at the same time, then
Maybe we can have less than 30 minutes for the break between the two sessions. And as
want some water? Yeah,
oh, that's just...
nooit 20 buttons.
Try to get a coffee or... I'm going to come and participate in your session, Sandra. Okay, yes.
I mean, we're in Italy. You'd expect it. It's not like we're in Switzerland or something.
Yeah. So, yeah, we see you stay busy. You have another.
I will stay in this room.
Good. We have some food there then.
You always have my support, Sandra.
Fantastic. Okay, but this work, we're in business.
Of course you are.
Tout le monde, ça soit fait.
Non, moi je suis discouraged. Je vais la nager et après pour ma session.
How many languages do you speak?
Just, you know, I cannot, I need to talk with you. Oh, this is, I cannot, this is the California bonus. And he's the one that developed
Fantastic.
Ja.
Okay. Great. That's
Ja.
very useful.
Maar ook de presentatie geven.
Yeah, so we have a better
This means yes. Yeah.
I had a lot of things to ask.
Yeah. Exactly. Yeah.
So, but of course,
Yeah, and there's a laser pointer.
Yeah, and there's a
Yeah, very
no,
easy.
no 10 buttons.
Going to presenter mode, do you know that or no? Maybe I should ask you.
Aquí está bien. Aquí está bien. Cambie.
Not in the mountains anymore now. Like there in the, was it 37? Yeah. There were years.
I kind of got out of all the ecosystem accounting. You guys had figured it out. So
We are working on that. Hi, Eileen. My colleague Eileen.
Hi, Roger from USGS. Nice to meet you.
So, you had a good trip?
Yes, yeah. Although quite a journey.
It's always
Yeah.
to get to the airport in Rome, but having
Yeah,
fast,
yeah.
takes some time to get there.
Yeah, I finally made it by train to the Frascati train station. I sat there for like 40 minutes just waiting to get a taxi to get up there because I missed the bus.
Yeah, there are some slots in between. Ah, you mean here from Frascati to
Yeah.
here? Ah, okay.
Like a ghost town.
Yeah.
So I did the Uber thing and it said
Yeah.
no problem.
No, you need
25
to-
minutes they're coming.
Normally you need to reserve it the day before.
Yes, I walked because for me it was walking to the bus or here it was.
Yeah, to here it's okay because it's down.
Yeah, but
Going
the
up
other-
you need a shower when you arrive back in the hotel. I did it a couple of times. Okay.
So we'll work together on weed next.
So,
You're deep into the weeds.
I am in the weeds.
Sorry, Bruno. Camilla Johnson is not coming.
Camilla Jensen,
The first presenter.
she's ill.
So we have one less presentation. So he gave us extra 8 minutes. As she
Yeah.
said. Don't get wild, don't get wild.
I know, but it's busy time. Help find your name list.
Goed. Ja, goed. Ja, ik moet nu een sessie even checken.
Ja, ik weet het. En stel dat het interessant is om te volgen voor mij ook, of zeg je wel,
Ja, ik bedoel...
dat weten we allemaal.
Ik weet eigenlijk niet wat de andere sessie is, want ik heb niet gekeken dat ik nog in deze moest zijn.
Maar dat weet nog wat ik is.
Dat is goed. Ja, we moeten straks even spreken van zo'n paar dingen nog die al besproken zijn.
Oké, die gisteren aan wat gekomen zijn.
Ja, nee, gewoon zo.
Ja, oké, dat is goed. Ja. Ik heb met Steven nog gebabbeld over de calls. Hij was toch niet zo happy om tegen 9 te trekken, omdat hij echt wel...
Ja, ik heb, dat was een van de dingen die ik met de GRC heb besproken, want in de 9 staat in de GRC moet meenemen. Maar je gaat die wist er niks van, dus die ging het wel aan Iona vragen. Nu, als hij er wat meer van wist, en dan is er nog die climate, EBV.
Van deze.
Ik heb ook even met Susanna even al besproken, ook Susanna is aan het kijken naar wat ze nu in die, maar ja, ze zegt ook van, dat is wel gezellig laat en dan doen dat de anderen. Hi, my colleague Aline, working in the biodiversity session.
Perfect. So we are getting started with the session. Unfortunately, we are a bit late.
Yeah, we have one speaker now. Yeah, from Sweden, she's not coming. We have a little bit.
That was a bit from 8 to 9.
Yeah, I even yesterday I need to give my presentation in another session and it's a bit of an extent, so I said don't come to me. I was not the one selected then. But I said indeed there were a lot of later. On the left side, the right side.
We should start. So I checked with the technical support already.
Okay.
So we have just Camila Johnson that is not here. Then we go. So we skip her. Yeah, and we're going to call everybody here. No, we don't have name. Hello, everybody that is presenting in this session. Hi, morning, everybody. We'll start in a minute. Can please sit here in the panel, so it will be faster the transition from one to the other. See, we have already a delay and such a short time. So please, everybody that is presenting, we invite here to the front. Thank you. Okay, so I think we are ready to start. Thank you, everybody. And well, sorry for this delay that we'll need to manage during the day. Still, for the presenter, we have these 8-minute rules in order to be able to have just one question for comprehension immediately after each presentation. And we really want to have at least 5 minutes of general discussions on that topic of ecosystem extent. My name is Sandra Luque. I'm a research director from INRAE in France, and also I work on the biodiversity applications and the ecosystem extent task force from CIOS with EGNES, the special French agency that you heard the presentation earlier this morning. So welcome to everybody, and I will introduce I pass the mic to my colleague Bruno.
Okay, thanks. Yeah, also welcome from my side. So I'm Bruno Smet from Vito in Belgium. I'm leading natural capital accounting and biodiversity team in our organization. And I'm the project manager also of the World Ecosystem Extend Dynamics, which you will probably hear also about in one of these calls. So I suggest let's not lose more time because we are strict on time. So we start already with the first talk, which is on the Global Ecosystem Atlas, which you have been introduced. Joanna introduced it yesterday, but Joanna could not be here today. But I'm pretty sure at least that David Patterson, at least, who is the project manager, can explain it well. So the floor is yours. So the first presentation, please. Okay.
Hi, good morning, everybody. So yeah, it's a delight to be here, and I'm going to be talking obviously about the Global Ecosystem Atlas. I'm going to talk about 4 things today. I'm going to talk about broadly what is the Global Ecosystem Atlas. I'm going to talk about what typology you were using. I'm then going to talk in general terms about the approach we're taking with the project. And then I'm going to conclude talking about some of the applications we foresee with the data we're going to be producing. The first thing to say about this project is that we are just in the beginning of it. We're month 1 of a 2-year first run. We expect the project to go much longer, so we're just at the beginning of this project. We are aiming to create a comprehensive global map of the world's ecosystems. This is a fully open data project, so code to documentation to everything will be open. We are harmonizing to the IUCN GET. I'll come on to that later. And we're spending a lot of time working with countries to get their data into the Atlas. So really, well, I'll come on to this later. The beta is already live. As you can see, there's a lot of blanks on the map, and so there's a lot of work to be done to fill in these blanks over the next 2 years. You just Google Global Ecosystem Atlas and you can find this and you can play around with it and have a look at it. But as I say, a lot of work to do yet. So the second point is what typology are we using? We are using the IUCN GET. The reason, well, I'll explain a little bit about that for people who don't know. There are 5 realms in this typology. Underneath that, there are 25 biomes. And underneath that, there are 110 ecosystem functional groups. So that's dividing ecosystems up by their function, like the ecological drivers like rainfall. There are 110 classes for this, and this is the level we'll be mapping at for the Atlas. Underneath that, the final layers, I think level 4 is estimated at 3,000 to 7,500 categories, classes, so that's obviously a lot. So that's why we're choosing to map initially at a level 3, because it allows for a harmonized global product, which is still manageable, but it's still useful for things like nature finance with enough granularity. So to talk a little bit about the whole project and how we're going with this. How we're running Atlas is, from the first point, we are basically searching for existing data sets and curating them. We have a library of about 300 data sets now, and then we are verifying them, testing them, and then they're going into a synthesis, and then they're going into the Atlas. So we end up basically with this mosaic of national maps which are updated with other data sets, and then they go into the Atlas. For those countries which don't have data, we're spending a lot of time working in countries with them, providing capacities, generating new maps, and then of course they go into the catalog, and then they go into the Atlas. So eventually we will end up with a complete picture. This is in a little bit more detail. So there's 2 ways data comes into the Atlas. Along the top row, it's existing data. We're obviously creating that catalog. We're doing a quality assessment. Then we're crosswalking it to the IUCN GET. That includes talking to the people who made the map to do the crosswalking with them, and includes talking to ecologists and experts to make sure that we're making the right decisions in that crosswalking. In some cases, you'll see on our map currently online, there are white spaces on the map for countries which have data, and that's because we were unable to crosswalk accurately. And then they get compiled into the base map. For countries which don't have data, we're obviously spending a lot of time building a global training data set which we hope to have 80,000 points in by the end of Q6, 2026. And then that's going into foundational models, et cetera, et cetera. That work's being led by JCU, Nick's Murray team out of JCU. And then obviously new maps get compiled. So the reason we're spending a lot of time working with countries and using existing data sets is because obviously there's a huge amount of data out there already, which is very valuable and is useful to use. And there is a lot of great national level data sets. So we want countries to use this product. We want them to feel ownership of this product. So we want to work with their existing data products and work with them to iterate them and improve them where necessary and crosswalk them. In all cases, the library of data which is building the atlas will also be available. So if you're interested in looking at the original data set, that will be available as well. So you don't have to use our version. Where this is all leading to is we end up with a base map, which will be at 100 meters resolution. So it won't be a global map per se. It's more this stitching together, this mosaic of different products together. There will, underneath that base map, be a lot of, and already is, a lot of technical layers for people who are interested into delving into this stuff to understand what's going on. Which, you know, I'm doing a demo later on today, which will have a chance to go into some of this stuff in more detail. If you're interested in it, please do come along to that. For those of you, well, I'm sure all of you have worked out where this is going. Obviously, by pulling together a mosaic of different data sets, you're going to end up with a very wide temporal base map. The reason we're doing this is just basically it's a very difficult task to get all this data together. There's a lot of in-country engagement which has to happen. So we're going to end up with quite a wide base map, probably from 2000 to 2024. This will be delivered by Q4 2026 for the world. After that point, we will look at obviously making more updated and change detection and other fun things. We're also exploring the idea of modeling backwards in time and forward in time and those kind of things. But just to say, that's where this is heading. In terms of applications for the Atlas, because we're an entirely open product, we expect our data to be used fairly widely. We expect it to be used by nations. We expect it to be used for global reporting. We expect it to inform the options for commercial standards, for people setting standards, which will inform what the business intelligence provide. Again, we expect our data sets to be used by business intelligence because it's freely available, and we hope, and we will be working very hard to ensure our data is as good as it possibly can be. And then obviously that data will filter down into corporates and FIs. We are working with academia and the NGOs to provide that data for, you know, just conservation research. And of course, we're entirely public facing, so you can get the data from the website directly from the API. We'll also make sure that the data is available in, you know, big platforms like Google Earth Engine and Living Atlas and Planetary Computer. And if people are interested, from large platforms to small, if they want to redistribute our data, modify it, do something cool with it, they're welcome to do so. So we expect the data to end up in a lot of different places, but that all rests on you know, this getting that data as good as it can possibly be. Yes, and that's all from me. Thank you so much.
Okay, thanks, David. Perfect in time. So I think we have time for one question. So somebody wants to ask a question to David? Yeah, okay. We quickly jump to you.
Hi, Peter Miller from Plymouth Marine Lab. How will you persuade the data creators to give over their data to an open platform, and then they will not be able to be part of the following usage of that data?
I think they can be involved in the project as we move forward. I don't think we'd you know, stop dialogue with them. So we have national accelerators at the moment where we're working directly with countries. At the moment it's the Maldives and possibly Costa Rica, where we're working with our ground teams and their ground teams, and a lot of work will go into building new national maps for them, which then they will have full ownership, and some of those products will end up in the Atlas. Yeah, so we don't see it as kind of like, you know, we're going to take and run away, as to say.
Thank you. So we are going to try to leave some few minutes at the very end. This is why we have all the presenters here. But next, I have the great pleasure to introduce Gary Geller from NASA Jet Propulsion Lab. And he's going to present some highlights of the work we were doing within the Ecosystem Extend Task Force within the framework of CEOS. So, Gary, the floor is yours.
Thank you, Sandra. So CEOS is the Committee on Earth Observation Satellites. It's basically all the world's space agencies. And if you're one of those people who aren't familiar with CEOS and you've been wondering, why is this CEOS thing at a biodiversity meeting, then this meeting hopefully will explain that to you. So CEOS, it's all the world's space agencies, basically. It was formed about 40 years ago with the purpose of coordinating civil space agency activities, things like closing observational gaps. The focus is really on societal benefit areas, such as biodiversity. It's not particularly a research-oriented organization. It has more than 60 members in it. And funding, it's interesting, there's no separate funding specifically for CEOS. All the contributions are in kind from the various space agency members. Focus areas, well, there's 13 focus areas. I won't list all of them, but they're things like climate and disasters, capacity building. There's also a technical component for data standards and so forth. And if I showed you the whole list, you would not see biodiversity on that list. However, starting a couple of years ago, it was recognized that biodiversity was probably a gap, and the response to that was to form what we called the Ecosystem Extent Task Team. So that was led by myself, Sandra, Roger, who's also here, and someone who's not here, Sean Levick from CSIRO. The Ecosystem Extent Task Team really wasn't so much about ecosystem extent explicitly. It was a vehicle for starting to discuss and explore ways that Earth observation and CEOS could engage more with biodiversity. We had two deliverables. One was a demonstrator that I'll talk about, and the other was a white paper. And then the follow-up for that, which I'll also talk about briefly, is called the Biodiversity Study Team. In terms of the demonstrators, we actually were fortunate to have funding to do all three that were provided. The funding was provided by various agencies. All three of them combined data from different types of sensors, which is important. It's something that's come up in this meeting so far. And all of them were also designed around data cubes, which is, data cubes are still sort of in the development phase in terms of operationalizing them. But we had three. One was the Hudson's Bay Lowlands demonstrator in Canada that was supported by Environment and Climate Change Canada. Another was the Great Western Woodlands. That was funded by CSIRO, the Australian Space Agency. And the third one was funded by CNES, the French space agency that Sandra led, and that was on tropical forests in Costa Rica. In terms of the white paper, you can download that. I think these slides will be available after the meeting. It's 38 pages of text mostly, but there is an executive summary that I think you'd find easy to read and hopefully interesting. What it does is to assess the potential for Earth observation support for ecosystem mapping and monitoring. And there were two key outcomes, one related to the challenges of doing that, and the other were some recommendations that respond to those challenges. So I wanted to just mention what the challenges were. And in terms of ecosystem extent, the way to discriminate one ecosystem from another is to look at the characteristics of each of those ecosystems, look where they're different, and then compare the characteristics that you can measure and use differences in those characteristics to discriminate the extent of the ecosystem. So the next four bullets tie into the ability to measure characteristics. One of the challenges and one of the recommendations is to combine data from different types of sensors, like SAR, which tells you things about ecosystem structure, and optical, which tells you different things. But combining those is very difficult because they come from different sort of social groups. The SAR people tend to be very engineering-oriented, for example. Ecosystem condition was another challenge. What do you do with a degraded ecosystem? What are you going to call it, and how do you categorize that? Effective use of time series was another one, and also dependent on how we discriminate ecosystems. And the last was the limited availability of higher level value-added products such as EBVs. But also reference data in a classical way of classifying ecosystems. Reference data is always in short supply, another challenge, and data accessibility and usability is another one. In terms of recommendations, I won't go through all of these. There were 8 in 3 different categories. One related to user engagement, another, there were 4 technical advances that were recommended, and those respond to some of the challenges I showed in the previous slide, and then capacity continues to be a challenge for utilizing Earth observation data. So the next phase, we delivered these things. The white paper and the demonstrator were delivered. The CEOS principles of the agencies were happy with that, and they said, okay, what do we do next? And the response was, well, let's form a study team to explore ways that CEOS should engage with biodiversity in the long term and broader than just ecosystem extent. So we're in the process of doing that now. There's 3 phases. One is, what are the needs that users have? So there's some interaction with the users there. Then with that understanding of user needs, then to sort of shop that around to the various CEOS entities, the agencies and so forth, and try to map the needs of the biodiversity community to the capabilities that the agencies and CEOS could respond to. And with that mapping, we can then assess the best way that CEOS should engage with biodiversity in the long term. And just to wrap up, I think our hosts at ESA have asked us to provide recommendations at the end of every talk. So this is my response to that. And first, I'll just point them to the white paper. There's a bunch of recommendations there. But I wanted to add one additional one, which is for space agencies to actively pursue more partnerships. And partners have complementary capabilities, and if we can bring those more into the sphere, such as for generating products that the space agencies aren't generating, then that would be, I think, a real step forward. So with that, thank you.
Thank you, Gary. Thank you very much, and thank you for this perfect timing. So, question for Gary. We have time for 1 or 2 questions. Somebody? Yes. To you. Sorry. This is sportive time. It's good.
Hi, Jeff Smith from Spectra Natura. Thanks, Gary. That was an excellent presentation. And I think you've sort of touched on the key things, that sort of Earth observation is mapping those characteristics of the ecosystems, but perhaps not ecosystems themselves. And I think maybe we need to have some kind of translation piece in the middle where we take the descriptions of ecosystems from the sort of ground point of view, and then these capabilities from the satellites, what satellites deliver. So, I mean, can you have you got any suggestions of what maybe that translation language might be in the middle of that process?
Well, probably some sort of machine learning model that can make the association between those two things. In my mind, every ecosystem is basically just a suite of various characteristics. They could be structural characteristics, structure, function, composition, phenology. There's this whole suite that every ecosystem has. So the more of those characteristics that we can measure from space, we can then map to the specific ecosystems. But it does mean that we have to understand ecosystems well enough to know what suite of characteristics this particular ecosystem might have. And that's where in situ data, I think, is essential.
Perhaps to add, in the session we have immediately after in this room, you will see some concrete examples and also work with in situ data for validation. And in fact, there's one of the demonstrators that is the one we developed for Costa Rica, but also we're transposing to other Latin American countries. So Jean-Baptiste Ferrer will be presenting this, but there's other examples and cases on, exactly answering, I think, Jeff, your question. But thank you, Gary. Thank you.
Okay, thanks. So our third speaker is Roger Sayer from USGS, and I think he's well known in the community, and I think one of the first ones creating, I think, an ecosystem map at global scale. So Roger, the floor is yours.
Okay, thank you very much. Happy to be here in this session on ecosystem extent. Ecosystem extent, nothing better. I've done a lot of mapping of global ecosystem extent over the years, and the question always comes up, is there any utility for these global top-down ecosystem maps apart from, global analysis, global context setting? Is there any utility for these products in some of these national applications? So here to talk about that today. All that work that you saw was done under commission to the Group on Earth Observations. That was in a global ecosystems mapping task, which had a nice and productive run from 2005 to 2023, at which time it was sort of replaced with the emerging Global Ecosystems Atlas initiative, which we just heard about. There's the charge, and I usually read that out because I like it, but I'm pressed for time, so let's go right to this slide, which is worth the price of admission alone. This is sort of the vision for all of this work that we've been producing. We start with what we call the EXUs, where the X represents the terrestrial domain, the freshwater domain, or the coastal and marine domain. So we have ecological land units, ELUs, EFUs, freshwater, EMUs, marine, ECUs, coastal, and we're working on EBUs, ecological benthic units right now. And then we sort of put those together and integrate them and then create these sort of reference level maps of world terrestrial ecosystems, world freshwater ecosystems, world coastal and marine ecosystems. A lot of work already done, just a little bit left to do on freshwater and benthic. Dangerous to start at the beginning when you only have 10 minutes, but there are so many definitions of ecosystems out there and so many approaches to mapping them. Tansley in 1935, he coined the word ecosystems. And then Odom in 1958 came along, and the CBD has a definition as well. And they're all really similar. They're all saying that an ecosystem is a complex of organisms interacting with their non-living environment as a functional unit. Incredible similarity, nuanced differences between those. And then there's different ways to map ecosystems by their structure, by their function, by their composition, or some kind of mixed approach. The definition that I like best is actually this graphic one from Bob Bailey. It shows that an ecosystem at any point is really a vertical integration of these structural elements, the climate setting, the terrain type, the organisms themselves, the substrate that they're in. And so we have used that definition to map ecosystems in this structure-based approach. And so the latest product was the World Terrestrial Ecosystems. We put that together as a combination of a spatial integration of world climate regions, of which there are 18, 6 temperature and 3 aridity. 6 times 3 is 18. So you have 18 world climate regions, which we integrated with 4 landforms: plains, hills, mountains, and tablelands. And then we had 8 sort of biome level vegetation land cover classes that we derived from the ESA global land cover data. And we put all those together to make these world terrestrial ecosystems. There's 431 of them. That's what they look like. Lots of resources, the anchor paper, the data, web-based explorers, story maps, etc. So here's that question again. Can these ecosystems be used by nations for ecosystem conservation status reporting, a la the CBD-GBF, and for ecosystem accounting a la the UN SEA. Well, let's talk about that. These are some of the considerations when you unpack that question. First of all, are we using the right classification? Is it the GET? We just heard about the GET is a reference classification framework for the Global Ecosystem Atlas. Are we using some kind of sanctioned mapping approach with those WTEs? What about the spatial resolution? Is it adequate? Are they accurate, current? Do we know the uncertainty? Are they available as data in the public domain? Let's look at some of these. On the classification, we have crosswalked the World Terrestrial Ecosystems to the IUCN GET Level 3 ecosystem functional groups. This paper it's in review right now internally as a USGS open file report. You'll be seeing that pretty soon. Here's a couple of graphics from that paper. Eastern kind of North America and Australia. And although you can't see them, all of the ecosystem types in those legend blocks are IUCN GET EFGs. And there they are, sort of side by side. And it basically, in the end, was a many to one type of crosswalking exercise. Many world terrestrial ecosystems belonging to one GET EFG. So I'm going to say yes on that, the IUCN GET. Did we map these in the right way? Well, there is no sanctioned mapping approach. I'm going to say yes there too. I have it from some people on the Global Ecosystem Atlas team that actually a country can map their GET ecosystems any way they want as long as they're using the target ecosystems from the classification. What about the spatial resolution? I don't think that these global data sets are really that useful for tiny countries like the Maldives, but for medium and large-sized countries, I think maybe, and we're testing that right now with the United States. We are using our World Terrestrial Ecosystems line work to map these formations. It's a level in the U.S. National Vegetation Classification, the U.S. NVC, which is the same as the IVC. And there's a paper coming out that says there's 80% compatibility between the IUCN GET and these formations. So, and again, out of time, so I'm going to say yes, 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 yes on the rest of those considerations. You'll just have to trust me. Another great thing about the World Terrestrial Ecosystems is we've just recently projected them forward to 2050 by going back in, projecting the climate inputs properly using IPCC compatible modeling. We didn't project the landforms because they're enduring features, and then we did project the biomes. This paper just came out last month on the 2050 projections. And basically, we're at a place now where you can query any pixel of land anywhere on the Earth and see what it was as a world terrestrial ecosystem in 2015 and what it is in 2050. And here, that location in the Sierra Nevadas of California was a cold, temperate, dry forest, projected to change to a warm, temperate desert forest. So it changed in both temperature and aridity, hotter and drier. That's pretty interesting functionality. You can do that anywhere. And the UN SEA thinks that these data might be useful for national ecosystem accounting because they call this out in the guidance as an alternative ecosystem classification with associated mapping with line work. And so then in conclusion here, we are marching along to finish these world ecosystems across the domains to produce reference level global ecosystem maps, which we feel will have great utility for ecosystem conservation status reporting and ecosystem accounting. And then I'll just throw this recommendation out there. I think that the Global Ecosystems Atlas initiative should consider using these world ecosystems, crosswalked to the get, for the top-down display and use in a manner similar to Google Earth and Google Maps. When you're way zoomed out, the units are coarse, but as you progressively zoom in, the units are replaced with the finer and finer. In the case of ecosystems, as you start zooming into countries, it could be replaced with these national ecosystem mapping efforts that are coming along and populating the Geoecosystems Atlas. Thank you very much.
Hey, thanks, Roger, for this inspiring presentation. We are running a bit out of time, but I think we can take one short question. So, yeah, okay.
Hi, thank you. I just have a very short question about the future projections. Are you reporting uncertainty, for instance, when you have your app, for instance, where you click on this particular pixel, for instance, and you see what could be the next land cover, for instance? Are you reporting uncertainty, and how do you account for the fact that species have to move for creating this new environment or this new ecosystem, and then you may have some delay or something, like some lags or things like that?
Yeah, we can report uncertainty for the modeling. And then the other question about, what about the biota, and is there a lag time before it might move somewhere else? We took a hit on that with one of the referees. And because we're defining ecosystems with a climate change component, we said, if anything changes, then the ecosystem itself changes. But the biota may not change or may not change quickly. There could be a lag, and we can't account for that in our work.
Okay, thank you, Roger. We need to continue, and we try always to keep a couple of minutes for our general discussion at the end. So I have the pleasure to invite Sander Mucha to the floor. Sander is for Wageningen, environmental research at the Netherlands, and he will be presenting us in situ data and for the European habitat mapping. So the floor is yours, Sander.
Yeah, thank you, Sandra, for giving me the floor. I will tell you a little bit about the importance of in situ data for European habitat mapping. And I'm doing that together with Stefan Hennekens and Stan Loss. And we do this work also in cooperation with the European Environmental Agency and Obsession, the European project Obsession. So the context, there's a strong, as you know, there's a strong decline in habitats. 75% of all European habitats are assessed as poor or bad. And therefore mapping and monitoring of European habitats is key. And improved mapping of European habitats is therefore our major aim. And the key issue is that a huge amount of well-distributed European in situ data is needed for training of the Earth observation classification. And much effort is needed on this. So the target topology for us is the UNIS habitat classification. It's a hierarchical and comprehensive habitat classification with 9 major habitat groups at the first level and more than 300 at the level 3. So we're targeting on level 3. At floraver.eu, you can find a lot of information on the individual habitat types. So this is done by the European Vegetation Survey together with the Vegetation Science Group. And for each habitat type, you can find a lot of information on the distribution, photos, but also on the species composition. So if you're talking about habitats, it's important to know to have knowledge about the flora and about its composition. So we're talking about, here you see an example for raised bog. You see the diagnostic taxa, the constant taxa, and the dominant species. So these are characterizing this specific habitat type. And this is just to show you an overview of the habitat mapping strategy we have in Europe. So next to the Earth observation, I just want to stress that next to the machine learning and deep learning algorithms that we have, the training data is very crucial. So together with CNRS, with Wilfried Touillet and with Sarah Simusi, we have been working on a recently European wall-to-wall map using 22 predictors, so a lot of Earth observation data, but also a lot of data from the European Vegetation Archive. And the quality of the map is very much reflected also by the quality of the in situ data. And if we look at the training data that we are using from the European Vegetation Archive, now with 2.6 million georeferenced vegetation plots, there are three limitations. There are spatial limitations, so not all areas in Europe are well represented. There are temporal limitations, so it's harder to get more recent data. And most important, maybe also the locational uncertainty. So if we are using data, more up-to-date data with a 10-meter accuracy, then we have a limited amount of plot observations available. And that affects our classifications. So that is why we also want to exploit the GBIF data, because that's also an important source of information on species. Here you see the density map of the European Vegetation Archive, just stressing that areas like Eastern Nordic countries, but also areas in Spain are underrepresented, and we need more data for those regions. So we can extract data from plant species data from GBIF. So we extracted 40 million GBIFs, plant species records, all related to the 300 UNES habitat types, about 4,000 plant species. And also in the EVA database, there's information about the plant species. And we can analyze the combinations of the plant species at the grid cell. So for example, at the 10-meter grid cell or at the 100-meter grid cell. And for those 52.2 million plant species records, we can look at the diagnostic species, the constant species, and the dominant species for each habitat type. And the value you see in the table are from the syntaxonomic tables, and the diagnostic species we give a very high weight, the dominant species a little bit less, and the weight for the constant species just 1. And then we can come up with a total value, and that value that says something about the likelihood that it belongs to a certain habitat type. So for the exploitation, we have developed a new software tool, the UNES Proxy Distribution Viewer. First of all, you have to select which kind of data you want to use. So do you want to use the 10-meter and do the analysis at the 10-meter grid cell level and from which year onwards? Then you can select your UNES habitat type. So all the UNES habitat types are in. And then you can set the threshold, and you can show for a specific habitat type all the locations. And on the lower right side, you see the green dots where you have the new potential locations where this habitat might occur. So next to the red dots, and sometimes the green and the red dots are overlapping, is where we are certain that there are ground observations from the European Vegetation Archive, but the green ones are the new potential locations. So concluding, new potential habitat locations can be found by exploiting the GBIF plant species combinations at the grid level with the new tool. Preferably you use the 10-meter grid cell level for the analysis. And the challenge for us is still which threshold value should we be setting for each habitat type. So our key message is With regard to operational biodiversity monitoring, we cannot monitor all species, but we can monitor the associated habitats with Earth observation and in situ data. And for good habitat mapping with Earth observation data and machine learning, it's key to have a lot of good in situ data for training purposes. And while the temporal and spatial resolution of Earth observation data are increasing a lot, in situ data is still lagging behind, especially if you're talking about the locational accuracy. So more effort is needed in the collection of in situ data to support Earth observation and monitoring. That's it, so thank you.
Thank you, Sander. Brilliant presentation. Thank you so much. A quick question for Sander.
Thank you very much. Thanks for the great presentation of a very complex piece of work. I commented on the terminology yesterday. We talked about that in coffee break. But I wanted to bring up another point, which is the uncertainty related to your results.
Yes.
And the uncertainty that is permissible in different policy use contexts. And so we need to distinguish, I think, between general distribution understanding at European level, identification at national level, which sites have species and habitats of great conservation value where maybe risk assessment is okay, and maybe there your data are still good enough. And then the management of Natura 2000 areas or general conservation measures targeted at preserving certain habitat types where you need to have the absolute correct location. And I don't think you can guarantee that with these data. I mean, no one could with European data. But I think this is important to understand when we, for example, tomorrow will talk about that we need far better data than this fantastic piece of work already is.
Yes. And I think we also have to admit that for very specific habitat types, the in situ data or the distribution is so rare that we completely will depend on in situ observations, and we cannot even detect them using remote sensing data. So the precision about all the habitat types is very important.
Okay, thanks, Sander. So let's move to the next one. So next is Ioannis Kokoris from the University of Patras. And he will explain about also an experiment, at least on mapping ecosystem extent and habitats. And I think you will come back on the importance of the in situ data. Yeah, right.
Thank you, Bruno. Exactly. Hello, I'm Ioannis Kokoris from the University of Patras. I'm here representing firstly the People EA team, an ESA project led by Vito. And I'm also here as an early adopter of this project, representing Greece, and that tried to benefit from the outputs and the methodologies developed in the People EA project in order to see how can we use Earth observation data in order to develop ecosystem extent, condition and services maps for ecosystem accounting in our country. So first, the project started by conducting a state-of-the-art review to identify how Earth observation data and methods contribute in ecosystem accounting until today, and especially for ecosystem extent regarding my presentation here today. After that, we tried to see what kind of approaches can be used in order to map ecosystem extent. We identified three approaches, the known top-down and bottom-up approach from EU and international datasets is a top-down approach, and national datasets contribute to the bottom-up approach. There is also a vegetation-centric approach, which is the one that we selected in order to develop our models and methods in the People project. that uses vegetation maps and land use and land cover maps and other data are integrated as complementary data sets. I will present you today the results of 2 case studies from Greece, my country, and Slovakia, where we tried to develop units level 2 and units level 3 maps for the beginning, and then translate them to the EU ecosystem typology. An existing habitat workflow originally developed in the project, in the Horizon project Europabon, was enhanced to generate the UNIS habitat maps. And these maps were the important step to distinguish natural ecosystem types at level 2 and level 3 of the EU Extend typology. This workflow trained a machine learning model using in situ reference data points that were provided by the early adopters. And these models were trained in a hierarchical way, and then the results applied in the total ecosystem accounting area of its pilot test sites within those countries. The most important is that those UNIS maps that were developed also included probabilities for each class of each tree branch. And then an algorithm was developed to select the final UNIS classes and provide the final classification for the whole area. Okay. This is another schematic approach about the modules that were developed and used in the steps of our methodological approach. As you can see, firstly we have the feature extraction module, then the feature selection and training module, the inference module, and then the post-processing and processing module. Of course, a change detection module was also contributed to the inference module in order to integrate also changes detected through the process. From the 2 case studies that I'm going to present you today, from the results of those 2 case studies, in Slovakia, we collected the early adopter provided data from the whole territory of Slovakia. And as you can see here on the left, you can see the EVA points that were selected to be integrated in our models. And on the right side, the final set of training points for Slovakia habitat mapping. When mapping at UNIS level 1, our model showed that the accuracy of mapping in grasslands, forests, agricultural land, and industrial or urban areas is very high. However, those classes are the ones that well represented in terms of amounts in the training data. Of course, accuracy decreases when modeling water-related habitats, such as peatlands or shrubland, as well as partially vegetated areas and habitat complexes. We should also here mention that those classes have the less training data. Regarding mapping at UNIS level 2, here we managed to map very well, especially the forest types. And however, in this level, mapping different types of grasslands was more difficult. And we have also here noticed many misclassifications of the modeler. However, this is likely due to the large amount of sampling points within the training data compared to a much lower amount for the other level 2 grasslands, the grassland classes. So, don't have a lot of time. So here is a level 3 map with a focus on forest types. The model applied here managed to really well capture the different forest types in Slovakia, and even capture the transition from the lower altitudes to the mountaintops, from forests to sparsely vegetated areas or grasslands, where this and this is important because in the maps already available for the country, those areas were mainly mapped as forests or as grasslands, and not didn't have any other classes among those two. So in general, we managed to achieve 90% of more accuracy for natural classes, except for the wetland and wet forests. And we have quantified on some reference sites with ground also truth data. Now, for my country, Greece, we used different data sources for field plot data, from Natura 2000 monitoring surveys, MAES surveys that were conducted in Greece through a nationwide Life IP project. And here are some results. The UNIS level 2 maps capture really well some difficult to capture ecosystems, such as Eastern Mediterranean mountain heath, or some screes, or some wetland types here in the western part of Peloponnese, which was the case study for Greece. Finally, accounting tables for the year 2020 were produced for this region. And in order to conclude, because I ran out of time, again, thematic resolution is dependent on field plot and field survey data, especially when using Sentinel-1 and Sentinel-2 images. We propose to follow a dual approach that will combine deep learning and traditional approaches, and the main point and the main finding is that we should manage to develop a protocol that will follow a common understanding among EO scientists and practitioners and vegetation scientists and ecology scientists in order to move forward. We need standardized feedback from the field to the EO models. So this is mainly one of the most important findings, and this is something that we are going to work in the follow-up project, the World Ecosystem Extend Dynamic projects, where we will try to streamline those methodologies and see how we can develop a consistent way to collect, provide, and integrate field survey data into EO models. For now, Greece already integrated those results as a pilot accounting scheme for terrestrial ecosystems. We are in close collaboration with our statistical agency, and we're looking forward for the WID project results. So thank you for your attention.
Okay, thanks, Jonas. I'm afraid we are a bit running out of time, so I suggest let's move on. I mean, Jonas is here during the break, so I mean, let's try to take the coffee break.
And during the week. So.
And during the week, so please contact him if you have some questions.
Oh, thank you. Okay, so we are moving from Europe, finally, to Tanzania. And we have Helga Wichley. I don't know, sorry, pronunciation. Great. That is going to make us travel a bit off Europe. Thank you.
Thank you. Thank you, everyone, for joining. I just want to present you quite a different project, a small one-year project that was funded by USAID to provide the assessment of mangrove distribution in Tanzania, basically as a foundation for development and implementation of management and conservation programs, and also as a basis for their national reporting needs. So it's a quite applied project, and I think it tackles a lot of the issues that have been raised in this conference so far. Just for the history, basically the management in Tanzania of mangroves dates back to the early 1900s. unfortunately, still deforestation of mangroves occurred. So in 1991, the first national management plan was developed, and for this an inventory was conducted using aerial images and field observations, and it not just only classified the mangrove extent, but also species composition and mangrove forest height. In one of these maps you can see on the right-hand side, and I'm sure a lot of other dusty drawers in government and research institutions hold these paper maps, and yeah, I just want to flag that they're really a treasure when you're mapping change over time. Just like in many other places, also in Europe, there's no long-term monitoring in place, so we have very fragmented and inconsistent estimates, and I just want to give you an example of mainland Tanzania. So the estimates really range widely, and this makes it really difficult for decision makers to know what is actually the truth and what to trust. And unfortunately, I really love Global Mangrove Watch, but in Tanzania, it misses a lot of the inland mangroves, which are most likely to change, and this is why we need a more accurate and locally validated data set. So within this one-year project, first of all, we digitized and kind of preserved these paper maps for the future. I will show you in a second. We did extensive ground sampling, including local expert knowledge that went into our satellite image classification. We used Landsat for the baseline of 1990. And then for 2023, we realized that Sentinel-1 and 2 gives us better results, but we compared it to Landsat-2 for consistency. Then we had a look at the gain and loss, so the change over the time period, and then also, really importantly, we broke it down to the administrative management blocks of Tanzania and mainland Tanzania and Zanzibar for the governmental agencies to be able to use these values. We share everything open. The project is not completed yet, so for example, the code is still to be shared. And because this group mainly worked remotely on it, we used quite a few apps, and I wanted to also show you some for the validation and communication. So just, I hope this video will work. Just an insight, there were around 30 paper maps, and we scanned them. And we also digitized, so vectorized the extent with all the attributes that were recorded in these maps, and now they're available online for anyone to use. For the input of the model, we used multiple sources. We used existing data, so for example, the same group was already in the Rufiji Delta in 2018. We did field data collection with this form. Welcome to check it out. We also, of course, took ground control points from the digitized maps that I just showed you, and also from higher resolution satellite images like Planet NICFI. And we also had more training validation points going in from the feedback from draft classification outputs. The processing was all done in the Google Earth Engine Python API. We basically used all available imagery that were in the catalog. As mentioned, Landsat Sentinel-2 and Sentinel-1. You can see the composites here. We created vegetation indices from them. I will show you in the next slide which ones we used. And for a proxy for phenology, we also used spectral temporal metrics, and then monthly time series for the radar and a radar vegetation index. And in total, these are the features that went into the different models we created. And just for the indices, we used general ones like NDVI, and then more mangrove-specific ones that basically take advantage of the shortwave infrared, where the mangrove have a distinct spectral profile. For the models, as said, we used the Google Earth Engine Python API. For 1990, we only had one model because we didn't have these awesome maps for Zanzibar. So we did one model, and then for the 2023 analysis, we had two separate models because there are some distinct features between the two places. And we also created a model for Landsat and Sentinel and then compared them. We did some post-classification filtering, particularly expert knowledge went in there, so we did some manual cleaving afterwards, and then most importantly, we vectorized it because we found this is kind of the format end users want to use the information. And last but not least, we used the Google Earth Engine implementation of Landrant to get some ideas of the year of loss and gain that we, in the areas that we identified using the random forest models. Keep in mind that we weren't able to properly validate these results, but they give us some indication of the general timing, as you will see in a minute. Just model accuracy, as they often are shown. This was before the post-classification process with 10% of the samples, and you see an overall accuracy of higher than 90%, but I really want to flag it always depends on what you put on the model you get out. So I don't really care too much about these results. It's really, does it reflect the real world that we want to map? And here's an example in black. I hope you can see it. This is the vector output that we got for 2023. And if we zoom in, we can nicely see that the model was able to distinguish mangrove forests from other coastal forests nearby. But as every one of you know, models, no matter how advanced they are, they do make mistakes. And for us, it was coconut tree plantations. Actually, all existing data also classified here in the Pangani River, the coconut plantations as mangrove forests. And here, I just want to flag that really take advantage of expertise to correct these classification errors. I just wanted to quickly show you the process we used. So we had this app, and basically we uploaded our draft classification output and then had this editable layer where experts could flag areas that we missed or that were in other way misclassified. Okay, I need to speed up. Also, this project is still ongoing, so we will do more communication, but we have an app already in place where you can have a look at the classification results, also the digitized maps. And we also provide higher resolution, for example, the NIC-free monthly mosaics. And you can have a look at the change. A lot of it is human-induced, especially the inland. But as you can see, we also have like natural changes in this dynamic landscape. And we can see quite nicely the results of mangrove restoration projects. And I just skip through them very, very quickly. Basically, I want to say that during this project, we learned that total numbers of districts, that's what governments were interested in, not the maps and locations. And only when these numbers make sense, they're interested in further insights. So maybe keep this in mind if you have something. Basically, most of the changes happened in the Rufiji Delta, that's the Kibiti district, and with the land rent analysis, we saw that really the last couple of years drive these numbers of change. We want not just to do research and impact real conservation policies, and thanks to the work of our Tanzanian partners, the government agencies want to adapt this data, so make it an official data set, which we're super happy about, and use it also for reporting, and hopefully it will also help to improve global data sets. And just quickly, next steps, we did a species analysis back in 2018. You maybe can see from the shift in colors, there's a huge shift in species composition, which will be really interesting to further analyze and also the drivers of mangrove change. Here just you can see the team and the contributions. And just sorry for taking longer, just some key recommendations, especially with the NIC-free monthly composite not being available anymore. We really need access to very high resolution services and also cloud processing environments. I don't know what might happen to Google Earth Engine, ground truthing catalogs and pre-trained models. I think sometimes even more important than the satellite images itself. And we need long-term monitoring indicator vector products for WWF can't do all the data themselves, so really to use them. Thank you.
Thank you, Helga. It's a great presentation. Thank you so much. Regrettably, we have no time for questions. You use all your time. So we'll go to our last presentation because as you see, the other session already finished. We have more presentations here, but Okay, so we'll go to our last presentation of the day.
Yeah, sorry, it's a rather crowdy session. As you can see, the table is not long enough to put all the presenters. So the last presentation is from Brianna Pickstorm from the UK, from University of Exeter, and she will tell something about biodiversity net gain assessment.
Thank you very much. Hello, I'm Brianna Pickstone. I'm actually in my first year of my PhD at the University of Exeter, and I'm here to present some of my early research of looking at integrating remote sensing and machine learning for biodiversity net gain assessments in the United Kingdom. So in order to tackle the biodiversity crisis and to no longer see a net loss in nature when we are looking at infrastructure development, countries around the world are adopting biodiversity offsetting strategies such as no net loss and net gain. And in the United Kingdom, biodiversity net gain became mandatory in February 2024. This approach seeks a more sustainability-focused development through the creation and enhancement of habitats following construction. And that means that all new development sites need to see a net gain of at least 10% within 30 years of construction. So in order to achieve this, ecologists need to be on the ground to look at baseline biodiversity assessments where they calculate biodiversity units, which essentially becomes a proxy for biodiversity. So we need in situ data where they look at the habitat type, the area, the condition, the distinctiveness, and the strategic significance. This is a huge feat for England to try and tackle, and at the moment, local planning authority surveys are showing that it's most likely that ecologists will not be able to assess and monitor every single development project. So this is where remote sensing is potentially going to be a huge push forward to support some of the more labor-intensive aspects of biodiversity net gain. One of those is through land cover classification and looking at the habitat type, the area, as well as being able to monitor that over time. However, the current land cover maps in the United Kingdom use the UK Biodiversity Action Plan classification scheme. So although this shows the ability of Sentinel-2, as both the UK Centre for Ecology and Hydrology uses Sentinel-2 data, as well as machine learning, they do not match up with the statutory requirements of biodiversity net gain, which requires the UK HAB classification. So this UK HAB classification has 5 levels, from level 1 being very broad to terrestrial to marine, to very specific of level 5. This brings me to my first exploration, is looking at how emerging technologies, particularly the use of vision language models, can be integrated with remote sensing, including Sentinel-2 and UK National LiDAR, to classify habitats to UK HAB level 2. So why look at using a VLM or a vision language model? This comes back to one of the questions brought up earlier about the text or the classification or the characteristics within an ecosystem. So when we do a standard image classification, it sometimes struggles with the complexity and the variability of real-world ecosystems. So a vision language model essentially brings in the image classification, but has text features incorporated within the model. This introduces semantic understanding of objects and their relationship beyond simple pattern recognition. This has been noted to allow for better generalizations across different habitat mapping scenarios. So if you think you're looking at a land cover classification in one area, you'll be able to see spectral changes throughout seasons. And it's been noted that these vision language models can potentially generalize across seasons as well as location. So if you're trying to scale this, a vision language model could potentially be the solution. But of course, this is a new emerging technology that really has only been looked at in hyperspectral imagery, as well as fine spatial under 5 meters. So I really wanted to see whether this type of technology could be used with Sentinel-2 and UK National LiDAR. So I'm lucky to be funded by an ecological consultancy, and I'm able to get in situ observations of their biodiversity net gain assessments. These are continuously going to be provided to me throughout my research, but at the moment, I've got about 48 kilometers squared of level 2. So these are the 8 different habitat types that I have access to, and this is provided as a vector file with all of those habitat surveys. In terms of my input data, I use a median composite of the Copernicus Sentinel-2, which essentially was within 1 year of the survey date, as well as the UK has national LiDAR at 1 meter, but this was downscaled. to 10 meter resolution. So my final input image data was a raster of 15 layers at 10 meter resolution. The next part is the text data, and this is one section that I really want to focus on in the research. So the text input at the moment was just the 8 levels of habitat classes, as well as the level 2 description, which is essentially just from the UK HAB classification handbook. But moving forward, I'm working with the ecologist this year to have a look at what characteristics and what type of descriptions actually best associate with that level 2 class to hopefully move forward and improve the vision language model. So when putting this into the model, you essentially have the area that you're looking at, which is split into a 13 by 13 pixel patch. 13 by 13 patch with essentially looked at about 130 meters on the ground. This goes through a vision encoder, which is a deep residual 3D CNN network. On your other side, I had the input text data, which essentially included a standard term of this is a multispectral image of the habitat class, along with the description from the UK HAB Level 2 handbook. This is processed through a text encoder, and what this essentially does is tries to assign meaning, as well as associate some of the words, like rivers and lakes would be more associated with water. This then gets put into the third feature of the model, which is a supervised contrastive learning or a shared semantic space, where it aligns the input image and the text data together and tries to push those ones that are less likely to be there further apart. So then you essentially have your input image and your text data aligned within this space. I ended up looking at 70% of my data for training and 30% testing, which achieved an overall accuracy of 93.81. But again, this kind of goes back with the in situ observations. A lot of my observations were from cropland and grassland, so I do still need to get more data from wetland, heathland, and shrub. I just wanted to bring up a few examples. So this is one area. You can see there's grassland with cropland underneath and some woodland and forest. And in terms of its classification, one thing that's difficult to see in this image is the rivers and lakes that are underneath that thick woodland and forest. So it was not able to pick that up. In this area, it is a lot more complex with the rivers and lakes. It also has areas of sparsely vegetated land, heathland and shrub, wetland, and very small patches of heathland and shrub as well. When we have a look at this, it can generally know where it is, but in terms of small little strips of the rivers and lakes, it still needs to learn how to pick those up. But again, this is those small streams, if you look back at the image, is quite difficult to see with the thick woodland and shrub. And the final one is a cropland and grassland environment. And again, it generally knows where those are, but the small segments of splitting up the pathways of urban environment, as well as the sections of grassland, it is still learning. So at the moment, you can see that there is a potential for the vision language models, and moving forward, it will be great to see how it can explore to be further used in UK HAB Level 3 classes. And my next steps is to evaluate how it can be used in the context of environmental and biodiversity settings, moving beyond land cover classification, and potentially looking at being able to differentiate between grassland that is modified and grasslands that are in good environment, and to test what extent vision language model improve automation and facilitate policy integration. And finally, this will be deployed with the ecological consultancy to allow for their monitoring of biodiversity net gain. Thank you very much.
Thanks, Brianna, for this very innovative talk. Again, I think we are running a bit out of time, so please contact Brianna if you want to know a bit more and you have some questions. So then I'll give it back to you, at least, for the conclusion.
Okay. Well, thank you to everybody for staying here. As you saw, the other session finished, and we need to set up this room because we took a lot of delay from the morning. I wanted to do a quick discussion, but as you know, everybody was. So take a picture of all of them. This is where all together. And please continue the discussion in the short break we have before we set up this room again, where you will find also more information, and you can also contact us. So thank you enormously for staying here with us until the very end. A big applause to all the presenters today. Thank you. have the discussion I wanted to have. Yeah, stay there. Yeah. So, yes.
chairs a session called Earth Observation Conceptual Approaches to Improve Biodiversity Monitoring. And so our first speaker is Gary Geller. And so I'm welcoming you here. Thank you.
Oh, thanks, and hi, everyone. I hope you had a good break. So I'll be talking about the concept of a federated system, but the talk is really about what users need and are they getting it? And that's maybe one of the drivers behind the concept of a federated system. So that's the question. What do conservation users really need? And there's a very simple slide here to try to capture in just a few words for my 8 minutes what types of needs they have. Well, obviously essential biodiversity variables and indicators are two big categories of need. And then the sort of the third one here, answers to the questions that resource managers may have. And those can be very specific. I'm working with species X and I need to know its distribution, or I'm managing ecosystem Y and I need to know what its condition is, and what are the threats to my national park? Those are very specific questions as well. Well, to understand what users need in the context of this federated system thing, we really need to look at an end-to-end workflow. This is a very conceptual one, and you can see on the far left we have raw data, in situ data, as well as remote sensing data. And as we move to the right towards the users on the far right, we have a series of progressions of more and more derived products. So the remote sensing data usually goes into a level 2 product like surface radiance, and from there can move into things like, when combined with other types of data, things like essential biodiversity variables, which for the most part, EBVs and some other data are really the raw feed for things like the biodiversity indicators that all these organizations on the right need, for example. The thing is, for space agencies, where space agencies provide most of their data, it's on the far left of this workflow. So we have the observations themselves, the level 2 products I mentioned, and then a little bit starting to move into some of those derived products a little bit, maybe VBVs or some other things like that. But what users need, a lot of users need, is on the far right end. So what do we do? Well, a coordinated suite of partnerships would probably help address this problem, because partnerships can provide complementarity to the observations and products that the space agencies can provide. So by using partners that provide that complementarity, it can help to fill in some of the data gaps that exist to the right of this little red circle here. So what's a federated system? Well, I'll just say it's basically an extended partnership, but a more complete description is here, and there's really 3 parts of this description that I think are important. It's, first of all, it's a system of systems, so independent components that are interoperating as an entire system. That takes advantage of complementary capabilities of the participants. I mentioned the value of the complementarity. And this is a key component, I think, of federated systems. Those participants provide, in a federated system, those participants are given enough autonomy for the components that they provide that they can kind of work out on their own and not have a conflict with the mission that their organization has with the mission of the system of systems. So this is really a continuum here. So on the far left, we have maybe the more traditional single system built by one organization, has a sponsor, lots of money, there's some requirements, somebody builds that and then operates it. So that's on the far left side. But a federated system, in the extreme case, is on the far right side, where it's developed by many organizations, where each organization provides a component that becomes part of this system of systems. Instead of being guided by some set of requirements that somebody puts together, it's really guided by some sort of shared vision that all the participants in the federated system have. In both cases, on the left and the right, you have to have some sort of design to tie things together. On the left, though, you can just build it. On the right side, you really need to grow it. And in the extreme case, that could actually be organic growth that you can't predict how it would actually happen. and capabilities could be provided in that way. Well, in this system of systems with different components, you really need to manage the interfaces, whereas on the left side, those interfaces are internal. And again, I mentioned autonomous components. So where in this continuum is best for our situation here in biodiversity and space agencies? And I wasn't going to actually stick my neck out on that, but at the last minute, for some reason, I added this arrow, and probably somewhere in the middle here, a little more to the left, would be maybe an area where some sort of hybrid system, like just partnerships and maybe a federated system component as well, that may be something that is at a practical level of federation that might be acceptable. But that's not going to happen during this meeting or even next year. This is kind of a long-term thing. What kind of members would be part of this federated system? I won't go through this, but you can see sort of the usual suspects, space agencies, subnational agencies, NGOs, and so forth. So each one of these entities could provide a component of the system of systems. I haven't shown the arrows because I don't know how they'd connect, but you can imagine that depending on who needs what, that these systems could interact. So a federated system then, there's all kinds of different architectures for a federated system, and then I mentioned already hybrids that are maybe completely organically growing on the right-hand side of that continuum, and then somewhere on the left, it could be some sort of hybrid combined with simple partnerships. But one of the key points is it does take advantage of the complementarities, and also because of the independence of the different components, it tends to be flexible and adaptable, which is very good in an environment like we have where requirements and needs are changing quickly. But that's only true if and only if it's well managed, because it can also lead to complications. And if we look at the challenges, we have all these partners working together or system participants, and sometimes there are conflicting needs and styles and so forth, so that's one of the challenges. The complexity of putting these pieces together that weren't ever designed to work with each other is another challenge, and that can lead to potentially data inconsistency. So managing interfaces becomes critical, and that's how you are more likely to achieve the data consistency that we would need here. My last slide then, a recommendation. I'll just say that I think it would be good if agencies would actively pursue more partnerships, and then once they have some partners in mind, and I think we all do, they may want to consider a role for some sort of federated component in this partnership, and hopefully then can lead to filling in some of the gaps in the right side of that workflow diagram that I showed. So that's what I have. Thank you very much.
Thank you very much. 8 minutes, perfect. We have time for a question. Oh. Oh no. Yes.
Maybe I want to have your thoughts, because we went into a bit in this concept of federated systems, and that was actually on the UN, on the systems of environmental economic accounting. And one of the notions you have not discussed in what you said, when you presented today, is what is the front end and what is in the back end. For example, what we decided working with the UN statistics divisions is that anything related to Earth observation workflows should stay in the back end, and we use their own system, the system they developed, in order to interface with their community, you see. So it's also important that even in the federated systems, not all part of the federated systems have the same role. And very often, I think, we as space agencies, we have to be humble in some ways and not pretend to develop front ends. We leave the front end for those who are interfacing with the community, who have their own community, and we provide the back end to them.
Oh, I totally agree. I think every community needs its own front end to interact with, and what happens, particularly for the biodiversity community, what happens on the back end, they may not care about very much. And they have their own things to worry about on the front end, I think, and that's why they want some of the products to the far right end of that workflow. So yeah, I completely agree. And I think, maybe the hidden message there, and maybe I should have stated it, is that, maybe the major role for space agencies is more to provide precursor products and a few global end products maybe, but letting partners and so forth fill in all those gaps that are on the right side. Space agencies don't provide many of the indicators that the CBD needs, for example.
Thank you. So I saw there was another question, but can we do it later? Yeah, thank you. We're running out of time, sorry. So we're now welcoming the second speaker, Victor Martinez Vicente.
It's a bit taller than I am. Okay. Okay. Well, hello, good afternoon, everyone. Thank you for inviting me to come over and speak to you about what we have been doing as a part of a collocated effort that the European Space Agency funded over the last 2-3 years. I'm coming here in representation of actually 4 projects. And trying to introduce to you a small overview of all of the work that we have been doing together. Well, not together, but in a coordinated way. And my first point here is that many of these things are way beyond my area of expertise. This is I'm going to be talking in less than 8 minutes about land, about marine, about coastal, and then about freshwater remote sensing products for biodiversity, so bear with me. So the idea that we, at the sort of end part of these 4 projects, there was an activity that was to provide a white paper overview, sort of high-level thoughts, a little bit more based on the results that we got from each of the projects, but then trying to combine them and create and do a bit more perspective thinking and what can we learn when we look at each other, which we have never done before. So one of the starting points was trying to find areas of intersection between the domains and the essential biodiversity variables. One of the projects here, Biomondo, produced that cube there, which is a simplification of what the reality is, obviously, because you just have a square mini compartments. But through that, we can see that on the bottom axis, you have the essential biodiversity variables as defined by GeoBond now and so on. And on the other Y at the bottom axis is the domains. In that area, we were looking at what variables, what intersections are common across the different domains. And then on the sort of vertical axis, you can see the drivers of change. And we also were looking at what drivers of change we could do with those, and all related to which essential biodiversity variables we could combine. So in the first example, this is coming from the terrestrial part. And there they were looking at the ecosystem functioning, and they were focusing on the primary productivity and how they can replace or use some of the temperature or other variables to produce primary productivity instead of using model outputs. And they actually improved. They were showing in some of the results that they were improving the spatial resolution of their estimates of primary production in forest. But then they were also able to look at variations with time of the land surface temperature and how is that related to effects that the bark beetle may have as an infestation. And then they were also looking at the changes in primary production. So here, for a person like me that comes from the marine environment, when we were looking at their primary production algorithms and they're looking at incorporating land surface temperature, this really reminded me what we're doing, or we've been doing for a long time in the marine environment, where we use sea surface temperature as input for our primary production. And we were looking at trends as well in the primary production part. So this is a plot from a colleague of mine at PML, where you can see this is the percentage of change with time in different areas. And this is one of the areas, one of the EBBs, where we identified a very, very strong connection between what we are doing in the ocean and what they are doing on land in terms of ecosystem functioning. The second example came from the freshwater community, and there they're also inputting lake surface water temperature to parameterize and improve primary production. And there, they were also looking at the changes in the time evolution of the primary production, which was something that we also looked in the intertidal, in one of the coastal examples. And there will be 2 talks in the marine part by this team in a couple of days, in Thursday morning, I think. So there we were covering the different areas in Europe and created time evolution of based on Sentinel-2 data with a very nice spatial and temporal resolution, and looking at the timings of the peaks of the spring blooms and how they change with latitude. So this is something, phenology, it's an important area of where we see a lot of overlapping between the 3 domains. And the final one, it's on the open ocean, and this is more about ecosystem structure. This was something novel for us, at least in the marine, where we are more, I like to think a little bit behind than it is in land, the part of spatial structure and how that changes. So we did some clustering of based on optical data or in fronts derived from temperature and so on. And we created some clusters that are changing with time. So the challenge here was to relate it to the biodiversity and then seeing what happens with time. We correlated all these different data from species richness on the y-axis to the chlorophyll from satellite and separated it to the dominant water class or the seascapes based on color. And we see that there are some things that are collocated with what we see as the changes that species richness has with phytoplankton biomass or so. So this is things that we then take into what we look at the seascapes, which is this regionalization that we did before, and we're beginning to see where are these changes in the structure of the ecosystem and what they may mean at the level of the species. And I think that there, from my part, I think we'll be very much interested in understanding what people in land are doing on a similar field. Here you will see just a comment. Here is at the beginning of the record. This is based on a climate change, I'm almost there, climate change initiative dataset. At the beginning of the record, you notice it's not that there is a huge climate tipping point, is the swap from sea waves being there or not being there. And definitely something that this type of investigation has allowed us to see better in our other data, so a bit of an understanding there. So we went and looked at the primary production, phenology, and seascape landscapes. We looked at the effects of the temperature and habitat change as main parts, and as recommendations, we thought that we needed to learn more from each other, so we hope that ESA incorporates some cross-interaction in future calls, that we will have we will find some new areas of intersection, either in space or in EBBs, and then that we will be able to align these calls to produce or common or harmonized common data or data sets that extend throughout or throughout the domains or and/or harmonized methodologies. And I think that's the last slide. So thank you very much. Sorry that I'm a bit late.
So our next speaker will be Jean-Baptiste Ferret.
Hi again, everyone. Okay, so here I will give you this talk about an Earth observation-based framework for monitoring tropical forest ecosystems in Costa Rica. So it's about ecosystem extent, condition, and composition. So I won't be too long on the context of the biodiversity crisis. I guess we are all aware of this. And to try to provide answers for this crisis, so we need some operational methods to monitor ecosystem dynamics through space and time. So Earth observation satellites, they provide key information for that kind of monitoring. But their operational application needs a certain number of things, including being able to handle massive amounts of Earth observation data, using scalable methods, able to extract ecologically relevant information, and being able to efficiently combine and compare in situ observation with Earth observation products. So the work I'm presenting here is part of an effort which is led by the Ecosystem Extend Task Team from the CEOS. So you've heard of it already in previous presentations. And so basically what is the main goal is to use Earth observation data to support critical biodiversity variables of ecosystem extent. So here we will introduce a demonstrator which was initially dedicated to mapping of the Costa Rican forest. So it was developed by INRAE and funded by CNES under the supervision of Sandra Luque. And so basically, why Costa Rica? Because it's a biodiversity hotspot with strong topographic and climatic gradients. We have more than 50% of the forest, of the land which is forested. And so this is a very interesting context for us to work on forest. And so here we will provide perspective as well and current limitation of the method and application to larger scale. Okay, so main objective of this demonstrator is to map biodiversity and floristic composition turnover over Costa Rica with Earth observation, so including Sentinel-2. It's mainly based, solely based on Sentinel-2 actually. And so here we aim also to assess conservation potential of secondary forests in human-modified landscape and to compare conservation potential of intact and disturbed forests, but it will be out of the scope of this presentation. And so we have a bunch of challenges, like more technical challenges we need to face. We wanted to use free and open data, software and products to ensure reproducibility, allow benchmark analysis, product validation, with the capacity to handle Earth observation time series. So we wanted to use cloud infrastructure and cloud-native applications. And we also have in mind the future missions that were presented earlier today, including hyperspectral missions, thermal missions, and so on. And one of the goals as well is to promote the use of Earth observation and save time and money for public data providers, method developers, and end users, of course. So, about this infrastructure. So I won't get into too many details, but basically here it's all based on data catalogs, so which are developed and using some standards like the stack standard for those who are familiar. So this infrastructure was developed in the frame of the DataTerra research infrastructure, which was introduced this morning by Philippe Maisongrand. And so basically, it's all based on cloud-native architecture, and what we want to provide is optimal interoperability between providers so that people can use either this cloud infrastructure or the Copernicus data space ecosystem or Microsoft Planetary or whatever they want, as long as the data is here, and then they don't rely on a unique provider. So that's what's the most important. And then based on this infrastructure, we develop a bunch of processing tools, quality control tools, deployment tools, and at the end, some applications. And so what we've been using here with this infrastructure were a few methodology developed in our lab, and the one I will focus on is so a method which aims at mapping spectral diversity metrics based on Earth observation data. So here I will talk about alpha diversity and beta diversity metrics, and I will get back to it very soon. So our infrastructure is online. It's currently in test phase. We are still not fully operational, but in a matter of 1 year and a half, I think we achieved something really nice, interesting, and hopefully really useful for the community. And so the goal is to provide some higher level information like cloud-free spectral indices synthesis from time series of Sentinel-2, for example, which will allow to describe key vegetation traits and also spectral diversity maps. So it's all based on standards, as I said, and the goal is to allow upload, download, so basically people can use it as a portal to provide their information to the community, or they can use it in order to get information. So it's also combined with software development kit and some plugins with QGIS, for example, QGIS, in order to make it easier for people who are not used to development. And now on the results. So here, as I said, we produce some spectral diversity maps. So these spectral diversity maps correspond to alpha diversity, which can be, for example, expressed as a Shannon index, which is quite used by the ecology community. And beta diversity maps, try to express floristic composition gradients. And so it will be displayed as these very colorful maps, and how to interpret it, basically. So dissimilarity in colors correspond to spectral dissimilarity. And hopefully, if the process is working well, we hope that this corresponds also to dissimilarity in floristic composition. So here you have the first results obtained for the Costa Rica with RGB imagery on the far left, and then the forest types which were provided by some collaborators, and then the alpha and beta diversity maps. So here we can see a bunch of colors. So as I said, validation is still ongoing. So one interesting thing is that you can see the green part is basically mostly driven by agricultural land because we didn't mask it here. And if we zoom in a more like a smaller location, you can see differences between mangroves and other types of forests, for example. So here we produce some continuous diversity metrics, and one of the challenges is to be able to relate these continuous diversity metrics to ecological information. So it's not a classification. We try to get something which is, I would say, higher dimensionality. And it may be an additional product for ecologists to work on describing ecosystems. So we've been working as well on Peruvian Amazon. So we run the method on Peruvian Amazon to map alpha and beta diversity, and we try to compare it to the floristic composition, which was provided by Chavez et al. In 2020. So here one interesting part is that we can start seeing some limitations of like Sentinel-2 imagery analysis. So here we have some relatively strong artifacts, but still we can see that there are some interesting patterns. And if we zoom in, we can actually relate to what was provided by Chavez and collaborators, except that we are using Sentinel-2 spectral indices for only a short period of time in 2014, while the colleagues used a whole lot of information and supervised machine learning. So one point is that our method is fully unsupervised, and so you can basically run it with no supervision. So another example on French Guiana, and here you can also see you combine artifacts caused by Sentinel-2 plus a very strong cloud coverage. So when you get the full product, well, I'm not proud of it. But you can see that if you check in more specific regions, you're still able to differentiate, for example, mangroves from other systems. So we think there's a potential, and we need to get better into harmonizing satellite data. And then just a last one, which is an illustration of a site which was showed by Musonda Momba yesterday in the opening session. So just to show that it can be quite quick to process. So basically yesterday when I saw that, her speak was really inspiring to me, and I thought, okay, let's check what's going on in this area. And so we could run it quite fast and provide these maps of these ecosystems. And so here we can see so the complexity of the wetland system with different types of vegetations. Well, and that's it. And so to conclude, here we provided a cloud infrastructure, hosting data, processing tools, and user-level products. It was a foundation for the CEO's demonstrator for Costa Rican forest, and we managed to produce large-scale maps related to biodiversity and floristic composition. We adjusted it, we applied it over French Guiana and other territories, so we can process massive data sets. And one point is that we need to anticipate the future standards for data for the next satellites like CHIME, SBG, and LSTM. And so our key recommendations are more remote sensing oriented. So we need free open data software and products for reproducibility, product validation, benchmark analysis, and intercomparison. We need to promote interoperability between Earth observation and biodiversity data hubs. So there were a few examples about GBIF, born in a box, so we're getting there. And I think it's really good for the community. And we will soon have all the tools we need to really make it happen. And we need more documented demonstrators for that. And then, last point, we need to improve data harmonization for large-scale tropical diversity mapping, as I showed. Thank you, and I'm sorry I was too long. But yeah, so no questions.
So then we have Andres Camilo, Zuniga Gonzalez.
Hello. Well, thank you everyone for coming. My name is Andres Zuniga. I'm originally from Colombia. And I'm a PhD student at the University of Cambridge. I'm going to talk to you about a project that it's in its very early stages that I've been working on with Josh Miller, another colleague, PhD student, supervised by Anil Anavapedi, on coupling ground-based sensors with remote sensing. But first of all, I want to ask you, what do hedgehogs have to do with a network of routers and urban systems? This is sort of like a pun that I will end at the end of the talk, but just keep that in mind. So essentially, routers, I'm going to talk to you about internet. Routers are like anchors that allow you to transfer data. So the power of the internet relies on the network, on how routers are like these devices that connect different places or houses, buildings, and allow them to transfer data. But we have natural anchors in trees. So trees are these like anchors that we use as humans, but also animals and other species use for living, and we can use them as a place to gather data. But first of all, how do we know where trees are, but do we actually know where they are? So what we came up with at the beginning, and this is like my part of the project. I am the remote sensing / environmental specialist. We tried to map all the trees in England using a LiDAR-derived dataset collected by the UK government, a 1 meter resolution vegetation object model we used to map all the trees. So we found almost 400 million trees in urban areas, which is not something that hadn't been estimated before. This was built using mathematical modeling of LiDAR data sets and big data technologies such as Sedona, Apache Sedona. But how do we like combine this with ground-based sensors? So meet the Terracorder. The Terracorder is this small device that we have been working on, which is like a tiny computer that can be modular, and we can attach different sensors, such as cameras or microphones, thermometers, or hygrometers to measure essentially anything that we want. And we can even run machine learning models on the device. And our idea is to place those devices on trees to measure whatever we can measure on ground and combine that with remote sensing data. So the idea and why I talk to you about networks is that these devices can actually communicate with each other and share information and schedule how they function. So the power of the Terracorder is that it has machine learning built in to optimize battery and collect data. So we can place that on trees to gather information. So like camera traps and monitor like human use of diversity in urban areas, which is my application part of the project. And our idea is to bring back this idea of the Internet of Trees, which was coined like 8 years ago, but didn't go further. And we want to like bring that back to use like trees as anchor points for measuring biodiversity in urban areas, but not only in urban areas. So this is something that's definitely not in the UK. We can use that animal tracking. And also because it can run machine learning models, we are working on privacy protection models. So like the devices, the camera takes pictures, and it removes like facial features from humans. So like we as users don't end up with private data. So in the end, like what do hedgehogs have to do with a network of routers in cities? Well, as I told you, well, trees are our anchor points, but essentially this is just an example of multiple things that we can do. So hedgehogs is just one, and if you didn't know, like hedgehogs are in danger in the UK because of habitat fragmentation. But we have the trees as anchors, and we can deploy these devices, the Terracorder, in different areas. So our team wants to invite you for applications to monitor biodiversity, not only in urban areas. This could be exploited in other ecosystems, which is actually what we are trying to do. Initially, want to deploy some of this in Cambridge because, it's the place that we work on. There's also like this work on the on-device machine learning model, because this device is like super tiny, and we have to like reduce the size of the models. And we want to, in the end, we want to create the Terracorder as an easy-to-use API kind of infrastructure that users can schedule to measure whatever they want. So not only monitor animals, but also monitor environmental variables for different applications. So the message is please reach out to me or the team to work together on deploying this. Thank you.
Thank you very much, Joel. We have time for questions if you want. Yes.
It can be placed they can be far apart because they use a technology that allows for communication. To be honest, this is I'm the remote sensing part. I'm not the builder of the device. But I can give you more details during the coffee break. Yep. Yeah. Yeah, so that's as part of my project is about where's the ideal place or where we can get the most out of trees in terms of ecosystem services and overall urban health. So that's my part of the project, and it's part of what I'm trying to do with the tree mapping. I've been working on this 330-300 rule for urban forestry that it's like a rule of thumb for tree urban forestry. And yeah, we're planning to like release this data set in the next couple of weeks as a paper. Yeah.
Thank you very much.
No time for content.
Okay, so we're getting to the next presentation from Marcel Schweider. Sorry.
Yeah. Hello, also from my side. My name is Marcel Schweider. I work for the Thun Institute in Germany. It's a research institute of the Federal Agency for Food and Agriculture. And today I talk on behalf of my co-authors that are listed here on the development of an OECD farmland habitat biodiversity indicator, which is purely based on remote sensing data. And I present to you the results of a pilot study for Germany. So just as a quick background, it's, as we're all aware, it's critical to understand the relationship between agricultural and land use and biodiversity to have a foundation for development of proper nature conservation strategies and to have an evidence-based policy advisory. So therefore, it's important to have a good monitoring system that we track changes and identify trends within the countries so that the strategies can be adjusted. So the OECD already has quite a good range of different social economic indicators, but looking on the biodiversity side of things, there's still a big gap, especially with a focus on agricultural use. So this is why the OECD came up with a white paper by the mid of 23, where they suggest a relatively straightforward way of how to implement such an indicator or develop such an indicator. And the main idea here is that it's based on the already available data on a national scale. So it should not be the call for a new survey that should be implemented on a national scale, but rather use the data that are already at hand, which can be from the field sampling, from digitization of aerial imagery, or using remote sensing data. And we decided to have a pilot study for that for Germany using the remote sensing data that we already have. And we followed this suggested workflow by OECD. So in the first step, we define the farmland habitats that should be monitored. Then we gather the land use data that are available on a national scale. And to each land use type, we assign a habitat quality value. This comes up later again, so keep that please in mind. The habitat quality value ranges from very low, 1, to very high, 5. Have the example of grassland use, for example. So we have an extensive grassland use, which is not mown at all, that has a rather very high use for biodiversity. If it's like an intensively used meadow with 5 mowing events per season, it's a rather low in this definition, so we assign a lower value. In the end, we combine these habitat values for each land use type, and then we calculate a weighted index based on the spatial unit we would like to report on. And in this case, we use 100 hectare hexagons, but this could be any spatial unit, like an administrative unit or whatsoever. Coming to Germany, we have this time series of land use maps here that we used. So we have a wall-to-wall classification of agricultural land, which in this stage then also defines the habitat we are interested in. It has a 10-meter spatial resolution, so it's based on Sentinel data and Landsat data, and a rather high thematic detail that matches quite well with the agricultural statistics for Germany. So we used this time series of 7 years of crop type maps and translated that. So we looked rather not at the direct use for each year, but at the time series and the crop sequences, if they are rather diverse or not. With the assumption that we have a diverse system, we have a more benefit for biodiversity. And we used this approach published by Clemens Jenecke et al., where we translate these crop sequence types to structural and functional types. So here's the example for the structural types. The x-axis, you have the number of crops. In 7 years, there can be 7 different crops. On the y-axis, you have the times, the changes that have been changed between the different crops in this time. And we assign these labels from A to I, where we say that if we have a broad range of different crop types and we have a lot of changes between the different years, this is very valuable for biodiversity. When looking at the functional types, we look at, okay, do we have rather, in these 7 years, do we have a higher share of spring and winter crops, or do we have and do we have a higher share of leaf and cereal crops? And in this example, the 5 in the middle would be in our terms, the most valuable for biodiversity, as we have a good mix of summer and winter crops and cereal and leaf crops. So coming back to the habitat quality values we talked about, we have this classification scheme going from very low to very high, and to each type I just described, we assign one of these values. This is the structural type, then we have the functional type, and the mean value of both we could assign to each pixel in our farmland habitat that we're mapping, and come up with this HQV, this habitat quality value map for croplands. We left out grasslands at this stage, and so we use another remote sensing-based product where we use dense time series of Sentinel Landsat data to estimate the mowing events, so how often was a grassland mown in Germany, and assigned similarly to this map for, we have the mowing event information for each pixel, and similarly to the crop types, assign a value. If we say, okay, it's rather not so often mown, we assign a high value of 5, and if it's more than 4 times, we, in this case, assign a value of 3. Then we also have some other land use types that are permanent crop classes and hedges that we also can assign different values, and in this case, for this example, we said, okay, when there's a lot of higher share of small woody features in any times, like hedgerows or coppices, we would rather assume they have a good impact on biodiversity, so they get a higher value. In the end, we combine all these maps. This is still on the pixel level, so we have for each 10 by 10 meter farmland in Germany, this information ranging from 1 to 5. And then we aggregate it in the final step to the spatial unit, and we chose the 100 hectare hexagon. As I said before, this can be any spatial unit you want to use. And we used this FHBI, Farmland Habitat Biodiversity Indicator calculation that was proposed by OECD. And then we came up with the first map of FHBI values for Germany. And here's some examples close to Berlin and the rivers, and in the pre-Alpine areas south of Munich, where we have very comprehensible spatial patterns, where we know we have intensively used areas, but also in interaction with less intensively used areas. So to sum this up, we have a rather comprehensive and straightforward indicator that is purely based on remote sensing data, and it can be frequently assessed. So we have all these maps on an annual basis, and we can derive this indicator regularly. In general, it can be transferred to other regions, but then, of course, we run into different problems, as we have maybe different land use types there, and we should probably include different data that might be relevant for this assessment. And yeah, then there's also the question how to assign these habitat quality values, because if you're looking on different species, different taxa, this is probably rather one of the highly debated points in this approach, because whatever species you look at, you might have different conditions that you want to promote here. So, and therefore, I'd like to invite you to our workshop, which we'll have today at 3 o'clock. Where we present with the colleagues from JSC. We tested this approach using the new VLCC product provided by EEA. And here we would like to invite you to discuss in the afternoon with us of what do we think of the general concept and how can this be improved and transferred in space and time. With that, I would like to thank you for your attention. And yeah, see you later.
Thank you very much. So we have time for one short question.
No.
Oh, no. Oh, thank you.
Paul Millen of European Environment Agency. Thanks for the presentation. One short question. Your crop type or land use maps or data sets are based on Sentinel?
Yeah.
How far they correspond to the farmer declarations? the annual farmer declarations with the agriculture parcels where the farmers declare the same crops?
You're talking the IX data?
Yes, in the IX data.
So we have this IX data for several federal states in Germany, and these maps are annually based. So for each crop type map, we have accuracy assessment. They are online available, and we assess each class separately. And of course, we have the broader land use classes that are important in Germany, all the cereals and so on. And here I would say we are ranging at like more than 85% accuracy. Overall, we are looking, it's more than 24 classes. For these 24 classes, we have an 85% accuracy. But honestly, there are some classes, when you're looking at soybeans, which is rather rare in Germany, we have very low users accuracies there. So this has to be kept in mind and depends on which data you're working with here.
Thank you.
Okay.
So we are now welcoming Selene Serna.
Hello everybody, thank you for coming. So my work is how do Earth observation foundation models help to predict multi-trophic soil biodiversity. And why we want to predict soil biodiversity? Because we want to address these critical threats like land use change, desertification, increased levels of pollution, and climate change. So the main goal of our research is to predict the abundance of 51 soil trophy groups in the French Alps. But we found some challenges. This first challenge actually is the reason why we are building our models. So it's the large unknown diversity of soil organisms. The second challenge is that there is technical limitations in species identification. And to overcome this problem, we will use the eDNA metabarcoding to compute the soil trophy group abundance. The third challenge is the lack of large and high-resolution environmental data sets. So for this, we will take advantage of Earth observation foundation models to extract features below ground. The fourth challenge is the difficulty of integrating diverse data types for soil prediction. In our case, we have images and also tabular data that we want to integrate. So for this, we will use the EOF models to extract embeddings, characteristics from our images and integrate it with our tabular data. So at the end, we have these three specific objectives. The first one is to make a comparison of 3 machine learning techniques, also compare data configurations. The second is evaluate the impact of orthophotos, and the third one is to identify the environmental drivers. So we have 3 groups of data. The first one, and the most important one, is the trophic group abundance. This was computed by using the metabarcoding eDNA process, and we get it from the observatory or CHOMP. The second group is environmental tabular data. As you can see, we have several variables. And if we focus more on climate and soil, we can see that we have 2 different types, interpolated rasters, and the other is in situ data. This is the highest quality data that we have in our data set. And we also have orthophotos from the National Geographic Institute. Here we have RGB and infrared. So in total, we have more or less 1,000 samples. So since our data set is small, and we want to also integrate images, we are going to use these EOF models to extract below ground features, in other words, or technically call it embeddings. We tested 2 techniques. One of them is SAT-DINO. The main goal of SAT-DINO is to predict the canopy height. But in our case, we are going to take features or embeddings from the penultimate layer of the architecture. And the other technique is DOFA. This technique it was developed to classify land cover, to environmental monitoring. And we are going to use it because it was trained in different satellite imagery, for example, multispectral, hyperspectral, SAR. So this is a summary of our methodology. We took all our environmental data and we arranged it in 4 data configurations. The first one, it considers all the variables, climate, soil, phenology, and landscape. But in this case, there are interpolated rasters. And the second case considers in situ data. This is a high-quality data for climate and soil variables. The third case is just considering the embeddings from the photos to make the predictions. And the fourth case is considering the embeddings integrated with interpolated rasters. We compare these three techniques, light GBM, random forest, and a multi-layer perceptron with an attention layer to predict the relative abundance of 51 trophic groups. These groups belong to 7 taxa: bacteria, fungi, protists, oligochaete, insect, metazoa, and colombola. And the question here is, can embeddings match or improve the performance of models based on in situ tabular data? So here we have the results. We can differentiate the performance of the models by the colors, by different colors. And also the metric used is experiments row. And by column you can identify the different data configurations. So light GBM and random forest showed the best performance as it was expected with tabular data. Also, if we check by taxa, we can identify the bacteria, fungi, and protists are the ones that presented the best performances. And in the case of oligochaete and insects, they performed poorly. More or less, it was for metazoa and colombola. And if we take the overall mean of the performances of the 51 trophic groups and we compare it by data organizations, by cases, we can see that the case 2, which is the one that considering in situ data, high quality, generates the best performance. Also, we can see that the embeddings from Sandino were the ones that give us better results. And if we check more in detail, we compare the embeddings and the in situ data, we can see that embeddings captures relevant information, but not enough to overcome case 1, 2, and even case 4. So the question is why? Why the embeddings are not getting better results? Here we projected the embeddings, Sandino embeddings, because it's the one that gives us better results. And we can see that there is some level of differentiation in the land cover, for example, coniferous and mineral surface. But also there is a lack of differentiation between shrubs and grasslands. So it means that embeddings lack granularity, the granularity that is needed to capture finer scale features to predict soil trophic groups. And if we analyze the relationship between in situ tabular data and PCA components of Sandino embeddings, we can identify in the first figure that the color gradients in the embeddings align with patterns in the tabular data components. It means that there is some data that is in the embeddings is also in the tabular data. It's a redundancy. This explains why we are not getting better results. The third objective of our research also was to identify the key drivers, environmental key drivers. So here I'm showing 2 cases, the case 2, which is the in situ data, and case 4, which is embeddings with interpolated rasters. And this is the relative importance of 4 groups for climate, soil, phenology, and landscape. And also I present in gray the Spearman's row, which is the performance metric that we use it. And we can see at first sight that the climate and soil are the main contributors in most cases. Also that soil variables compensate the absence of embeddings in case 2. And landscape contributions is not so big. Phenology also is more important for specific trophic groups. So as conclusion, we can say that there are group-specific prediction challenges. Also the tabular data performs better, continues performing better. But embeddings also capture partial information, and for this reason it could be considered as an alternative when there is no in situ data. So for future work, we are planning to explore more multimodal EOF models to integrate environmental data below ground features. Also to model interdependency of trophic groups and investigate the feasibility of incorporated high-resolution remote sensing data, for example, like Sentinel-2 meters. And these are our 3 recommendations for the conference organizers. Thank you.
Thank you very much. We have time for one question. Oh, there's one over there.
Really interesting talk. Thank you very much. I was just wondering, you talked about multimodal EOF at the end. What are you thinking of doing there? Some structural satellite imagery? Is that the next thought to improving the EOFs?
Yes, we would like to explore more multimodal EOF models. Because, for example, we found DOFA. DOFA integrates different types of satellite imagery, and this is beneficial for us because we have RGB images, but also we have infrared layers, so we can explore, and other EOF models could be interesting also for us to extract more below-ground features, more specific below-ground features. Thank you.
Okay, thank you. So our next speaker is Samantha Suter.
Hi, everyone. Oops, sorry, I already pressed too soon. I'm Samantha Suter, and I'm currently based at the University of Neuchâtel, working on the BioMoney project, and we're currently looking at scaling up island biodiversity monitoring with remote sensing. So the BioMoney project stands for Biodiversity Monitoring of Island Ecosystems, and we're specifically focusing on oceanic island ecosystems because of the high levels of rare and endemic species found in these locations. They're also largely disproportionately affected by anthropogenic disturbance, for example, but then also often not considered in international and long-term monitoring initiatives. So the project consists of 7 working packages in total, and we specifically are looking at the remote sensing techniques for increasing the spatial scale of this biodiversity monitoring. So our working package objectives consist of 3 main things. The first is to sort of develop new methodological frameworks for this upscaling of monitoring, specifically the essential biodiversity variables. So this includes some framework development that can be used for stakeholders on the ground and in these locations. We then also want to integrate both field-based data that we have from a series of plots, as well as remote sensing data, both from ground remote sensing as well as satellite remote sensing. And this is so we have a really all-encompassing picture of the different elements of biodiversity for these areas. We then want to look at tracking changes in the different essential biodiversity variables as well, both spatially and temporally across these different island ecosystems. So the project's still very much in its early stages at the minute, so we're only really still on Objective 1. And specifically, what we're looking at is if we can use or adapt any remote sensing techniques to increase monitoring beyond forested ecosystems or habitats. So at the minute, we're focusing on the EBV of ecosystem structure, and we're looking at structural complexity. So we focused on this concept of structural complexity with a metric that was derived for forest habitats, which incorporates this ENL, which is the vertical stratification of the habitat, as well as this mean fractal dimension, which incorporates the horizontal space occupation of the habitat as well. So I do feel like a little bit of an imposter because I will be largely talking about terrestrial LiDAR data rather than satellite data at the minute. So we focus on taking terrestrial laser scans and computing the structural complexity index from the LiDAR data. So at the moment, we have been able to visit Tenerife, and we surveyed 5 of their key habitats, but we were lucky to have 2 different communities for the coastal scrub, which we can see both the communities at the top of the image. We then also surveyed a thermophilus forest, a summit scrub, a pine forest, and then a laurel montane cloud forest as well. So we used a network of plots that already exist on the island, and we were able to conduct terrestrial laser scanning within those areas. So our initial results so far, the idea here is not necessarily to focus on the actual values of structural complexity, but to really think about what this actually means. So of course, when we're looking at if structural complexity has those same elements within both the lower lying habitats as well as the taller habitats. We wanted to see if the structural complexity index could actually differentiate the different types of habitats. We were able to see that there was quite a clear differentiation with the different structural complexity that was computed for these areas. And then we put the different elements of structural complexity into a PCA to sort of understand what this actually means. So for example, we can see that ENL, which is that vertical stratification, was really more prevalent, of course, in the taller habitats, such as the laurel forest and the pine forest. And then this mean fractal dimension, which was more relevant in the sort of lower lying scrub habitats, which may seem obvious, but we just wanted to kind of understand if we could still, essentially utilize this method for habitat characterization of the structural complexity in these areas. So essentially then, what does this mean? When we have a point cloud, for example, the small insert at the top there is a point cloud of the pine forest, and I think looking at the structural complexity, it's quite obvious. You see this not only a dense point cloud, but also quite a tall point cloud. But then when we look at the point cloud next to it, the larger image, it's actually one of the topiable coastal scrubs. And at first glance, you might think that it's not very structurally complex, for example. It's quite short, it's very sparse. But actually, when we zoom into the image, you actually can see with the different individual plants that you actually have this really dense point cloud for the individuals. And in the images, we can actually see that this is largely based up of its high branching architecture within this species. So we were finding that, of course, the components of structural complexity are additive. It's both this combination of the horizontal and the vertical space occupation. But actually, it's still very relevant to be surveying these lower-lying habitats, which these metrics often aren't developed for. We did find some limitations in the use. We still found some issues with any of the plots where the average height vegetation height was below 1 meter. But potentially, this still expands the range of use of the structural complexity index. So we really want to take home the message that it's not if we can adapt these different metrics or methods, but how can we? So the next stages of our specific working package are then to look at this scaling up. So of course, the terrestrial LiDAR data is still quite localized, but we then want to see if we can align this with any UAV captured LiDAR data and then potentially satellite data from JEDI, for example. We're also already looking at potentially expanding the forest integrity index to our areas, and then also seeing if we can look at the full waveform structural complexity index from JEDI to see if this aligns with the TLS data. We then want to look if we can link ecosystem structure with our field-based biodiversity data. So we already have tree species inventories, data on biomass, and so forth. And then finally, we'll be looking more into other satellite products for mapping and monitoring of the essential biodiversity variables that move beyond ecosystem structure, so ecosystem functioning and community composition, for example. And then for our recommendations, they're not very new, or it's what's been iterated throughout the conference, but of course we want products or metrics that are adaptable and transferable to wider range of habitats, as well as to be able to incorporate the different elements of biodiversity. We also want to push for open science, of course, and have a greater availability of these products, which would hopefully allow any limitations in certain methods to be addressed and also improve accuracy of these things. And then one of the real key points of the BioMoney project is that we want these frameworks and these methods to be used by the stakeholders on the ground who are conducting the monitoring. So we want to make sure our workflows are user-friendly and basically understandable. Thank you very much. I'd just also like to thank our project partners and Biodiversa and the SNSF for their support, and further information on the project can be found on the QR code. Thank you.
Thank you. One very short question, perhaps? No? All right. Well, and thank you very much. In the interest of time, so we've got 2 more presentations left. The next one is Gabriela Scheepman-Strup.
Well, good afternoon. I guess that everybody understood in the last couple of weeks that the Arctic is a hotspot, even for those who do not believe in climate change. And actually, if we look more closely, climate change is still the major biggest challenge, because the Arctic is actually warming 3 to 4 times the global average, and we expect major biodiversity and ecosystem functioning changes. And these are impacting the Arctic, but actually also the entire Earth system. 7 out of the 9 global climate tipping points are in polar areas or closely associated with polar areas. And we expect changes ranging from biogeochemical cycles to indigenous peoples' livelihoods. Well, how well do we actually know this Arctic biodiversity and its change? There are major efforts by several organizations. I would especially like to mention the Arctic Council Conservation of Arctic Flora and Fauna Working Group with its Circumpolar Biodiversity Monitoring Program. However, there are major gaps still, and I want to convince you now in the next few minutes that there is an interesting opportunity coming up where we can make better use of remote sensing data together with improved in situ data to actually improve and better inform management and policies in and for the Arctic. Well, a few of the points I wanted to highlight in the next couple of minutes are, despite efforts, ongoing efforts, for example, decades of NDVI time series analysis that have shown greening and browning, and then browning and greening in the same place, we actually don't really understand the underlying processes very well. Then further, as we've heard several times now as well, it's the same for the Arctic, we miss a solid baseline and repeated surveys of most biological taxa. So actually, how can we assess change if we don't even have a baseline? And then we still focus on climate warming mostly when we think about changes, but there will be actually other drivers in the new Arctic. We are talking about climate extremes, fire, industrialization. I want to bring up climate intervention here as well. It's a hot topic also, and we don't really know how it would affect the biology in the Arctic. And these are really important drivers that are important and need to be considered for biodiversity and ecosystem functional changes too. Unfortunately, we actually do not have these data sets, and this has major implications. For example, we showed in a study that already by 2050, most of the threatened vegetation types are not being protected by the current protected areas, because those are all rather in the southern areas instead of in the north, so they will not serve as climate refuge even already by 2050. It is not enough to look from above, from the satellite perspective. We need the understanding from the ground. And I want to illustrate this with this example here. I talked about complexities of the greening in the Arctic. At our research site in Siberia, we have no trend in NDVI over the past decades. What you see in the field is the picture on the left-hand side. So actually, we see degradation of the permafrost. The dry vegetation is actually sinking in, is decomposing. The wet sedges are taking over. It means we are losing lichens for reindeer. It means we have increased methane emissions. But on the other hand, we have more area, more water-covered surface for wetland birds. So multiple changes going on, even though we actually do not see a trend in NDVI. We had looked into this in a drone data series that we captured from 2014 to 2021. And you can see this dynamic landscape, and it's actually not just in the XY dimension, but we use structure for motion and also could show that we have elevational changes going together with biodiversity and ecosystem functional changes. So this is one of the points where we really need to do better. We need higher resolution. We also need better spectral information to be able to capture such phenomena. What about the ground data? I'm really happy that the EVA, the European Vegetation Archive data, was introduced this morning as a validation for habitat mapping. but also a training data set. We have a similar data set in the Arctic Vegetation Archive, with many plots potentially identified across the Arctic that we can digitize. We even added the Russian Arctic. However, we do not have repeat data there, and that's one of the problems. On the other side, there is the International Tundra Experiment with repeat measurements, but you can see the spatial distribution is not optimal, and it will not get better over the next couple of years, I guess, with the Russian situation, because we simply miss data from the Russian Arctic in terms of species compositional data. I talked also about new drivers. So the Arctic Tundra Experiment really is focusing on warming and how the biodiversity will react to this warming. However, warming is not the only thing that is happening right now. There is strong industrialization. We showed last year that across the Arctic we have about 5% of the area that is already lit by human industrial activity mostly. Only 15% of this lit area is actually tied to settlements. The rest is industrial activity. In some areas we have 30% of the area covered by light already. And we pressed the submit button today actually for a study that shows that also fire occurrence is much higher in these lit areas, namely 2.5 times higher compared to kind of natural areas. So definitely an area of concern. Fires will have an impact because fires are not burning equally, homogeneously across the Arctic. This again from the Siberian Arctic, we have vegetation patterns, and these vegetation patterns are burning heterogeneously. And if you would look at this from Landsat, the burned area product, this is the map we get if we do the same analysis with PlanetScope data, 3 by 3 meters resolution. We see these patterns are very different. We are actually underestimating, in fact, the burned area with Landsat in the areas that are kind of burning. And we are missing the important patches that have not been burned within burned area, because in terms of ecology, they are the ones that serve as seed banks to recolonize the burned patches. And actually, these fires are also really ecologically important and climatologically important. Of course, a major positive climate warming feedback through carbon emissions, especially because of the carbon-rich soils we have in these areas. But also, there seems to be indications for stable state shifts of the ecosystems, moving away from lichen-dominated system over time into shrub-dominated systems. Well, these are not very good outlooks, and we definitely, I hope I convinced you that we definitely need better information across the Arctic, and there is a unique opportunity coming up actually to gather more information, and this is the International Polar Year, which will happen in 2032-33. You think that's far away, but logistics are difficult in the Arctic. They are difficult, even more difficult in the Antarctic. We need to standardize, to coordinate between the poles. So it's really time to get ready and also especially discuss with the Space Agency how they can support the generation of new products and what kind of validation data on the ground we need. So the IPYs are usually only every 50 years. The last one was 2007-8, so definitely it wouldn't be up right now, but there was an announcement that the 5th International Polar Year will actually happen already much earlier. And here is the concept note saying that we really fear such dramatic consequences that we already should have a new International Polar Year after 25 years only. So it will actually happen in 2032, 2033. And we are not just waiting for it to happen. There is this planning of a ramping up of IPY projects that you see nicely displayed over in this graph. So definitely it's time to get ready now. Well, IPY will not happen by itself. It is really a community engagement. It's a bottom-up process. It's how it was always defined, and it will continue. So here are a few of the principles. Really, stakeholders should be involved, the users should be involved. It's really about co-designing research programs and really allocating funding to this important activity. We started with a small activity already, trying to reduce the time for vegetation plot assessments. Usually we need about 1 hour to do one plot. If we are flying out by helicopter, have 4 hours, we have 4 plots, which is not a lot. So I think it's useful to think about new ways to monitor vegetation, for example, combining with eDNA and drone data. And also making sure that not only botanists can do this validation. So I'm happy to talk to other people from other ecosystem types as well, how to best really do the validation of habitat maps. Well, I want to end with a few key recommendations. I think it's really important to first evaluate what expected changes we have across biological, spatial, temporal scales. What do we actually want to measure? Because we cannot measure everything during the International Polar Year. We should sit down together with indigenous people and actually ask them what they think is important to monitor. I know fires is very high on their agenda, for example. We need to develop common measurement protocols across the Arctic and Antarctic. I'm especially thinking about polar deserts that are occurring on both sides. And these protocols should also be accessible to people who are not specialists in the field. So actually we can profit of the hundreds or thousands of people who are out there, the atmospheric scientists, the marine scientists, everybody, to collect data. And finally, I mean, you've heard it all this morning in the session about the new sensors. There will be a suite of sensors. There will be CHIME, hopefully, SPG, Landsat Next Generation. So it's actually a perfect timing to profit from this new sensors that will be out there. And in this sense, I hope it will be not only cryospheric International Polar Year, but also a very biodiverse International Polar Year. Thank you very much.
Thank you. I think we should probably move on to not, yeah. So our last presenter is Julien Radou.
So, good night, everybody. This is not a picture of my stomach, but this is a picture of, taken by a satellite of the city of Boston. But this satellite was designed to take pictures of the day, and this is what you see if you take a picture of the night. Of course, I'm cheating a little bit, because if I do some enhancement, this is what I can see. So you can enhance, but you see that the signal-to-noise ratio is very bad. If we want some data about night, then we need to use VIRS data, where you get a data at 500-meter resolution. That can do a lot of things for sky glow, for instance, but for some biodiversity application, it is not enough. So my talk today is a bit challenging the space agency to see if they can build a satellite to get images of the night wall-to-wall for maybe the year 2035 or 50, I don't know, but one day. Why is this useful? Because the light, the artificial light, affects biodiversity at a very small scale. We can see in the lit and the unlit areas very big differences in terms of biodiversity, and those differences will change depending on the species that you observe. You can have local disruption, like the species will not stay where there is light. You can have a concentration effect where the species are attracted by the light. So you have more species under the light than in the surrounding, and no real impact on those surrounding. And you have the trap effect that is more annoying for biodiversity, where you have a negative impact on the lit areas and also on the surrounding areas, because species are attracted and then they die because they don't find anything to eat where they should have. So we need a connection between the small areas of lit area, where you have more artificial light, and the knowledge of the habitats that are under it to get information for the species. From the in-situ data, we have more and more data that are collected. We have more now some traps to get with AI the information about the presence or absence of different species of moth. We have some bat detectors that are now very easy to acquire, and we have about, I think in Europe, it's about 7 million data about bats now that those bat detectors are available. And we also have trackers, accelerometers to see the behavior of some birds, night birds, during the night to understand better what they are doing. But if I look and I want to connect those information with the VIRS data, it looks a bit, well, coarse. Of course, there are some solutions. Currently, for instance, there is the Jilin 1A data, where there's the same area as what I was showing with the VIRS data. You can see the lamps. So you can see this information, and we can try to map the different types of artificial light. Those types of artificial light also have an importance because some studies showed, for instance, that if you have a LED light, it is not the same impact on biodiversity that if you have a sodium light. So the color of the light will have more or less negative impact on the biodiversity, and it's important to be able to classify that. So we try to classify that on the Jilin data. We reach about 75% accuracy of the detection of the different lights, and you can see all the spots where we have the detection of the lights dropped over an orthophoto of the area that was mapped. Those maps can be done because we have very specific spectra of the light, so we know exactly what we are looking for, and it would be easy to detect that. Nevertheless, we have still issues with those kind of data. The first is that it requires some specific information to get geometric correction. And we also have a lot of false negatives that we have to confirm, but it's difficult because we have information where the light poles are, but not necessarily if they were lighting or not when the image was taken. We saw that some light could not be visible because they are hidden by obstacles like trees. They are under the trees, so we don't see them from the satellite. We have also problem with clouds, and for many times, unknown reason, we don't know exactly why they are not appearing on the images. And when we look at the overlaps, we see that sometimes they are visible, sometimes they are not visible. So 70% of animals are active at night. So for biodiversity, it's important to have this kind of information. The two satellites that are currently providing data of nights at very high resolution are approaching end of life. So what's doing next? I'm really looking forward to the CEO 3D satellite to have, again, a possibility to have image at night. But those are satellites that are very costly to operate because you get the long time observation to get the photons. So maybe we could have a satellite that is a better sensitivity so that we can have wall-to-wall mapping and repeat the coverage of that. So probably 10 meters is good because if you get larger, you don't get more photons anyway because the light is about 10 meters around the light pole. And we need blue, green, and yellow bands, relatively large to get more photons again, to be able to distinguish between the LED and the sodium images. That's it.
Maybe we have time for one question. And if not, yeah, I guess it's lunchtime. Thank you very much for coming to this session. And then we are closing now. Thank you.